So good evening, everyone. So is audio video clear for all? Okay, right. Somebody maybe very one or two members saying audio is low. That may be from your side also. You need to check because it is clear for everyone. Okay. Okay, right. So the last class we started the operation of transformer. That is first we have seen ideal properties. No. So mainly we have five ideal properties. Complete transformer is mostly depends on these five properties only. So one by one we will take. So one property we taken yesterday. So what is the five ideal properties first? First one is the permeability of core is infinite, but practically it is never possible that infinite permeability. So we have only finite permeability, but not infinite. Okay. Next, second ideal property is what? The iron loss of transformer core is zero. But is it possible zero iron loss? Never. So this is ideal. Okay. Next, third one is resistance of winding zero, and fourth one is leakage flux in transformer is zero, and fifth one is what? The shape of BH curve is linear. But practically, what is the shape of that BH curve? It is a non-linear curve called hysteresis curve or hysteresis loop. That is okay. Now, first one we have taken yesterday, operation of transformer with a finite permeability because infinite is not possible. And there, what we got from that point? Infinite permeability case. Due to finite permeability, when we give supply to transformer under no load also, it is drawing a small amount of current. Under no load also, it is drawing a small current to produce flux in the core. Otherwise, if you don't give any supply, there is no flux in the core. Now, once you given source or supply is given to the primary side under no load, then it is drawing a small current. Actually, if it is ideal transformer, no, as it is no load condition, what is the current drawn by transformer should be zero. It should not draw any current, no output, no input. But practically, it won't happen. Even under no load also, it will draw a small current initially. That current we call first magnetizing current. Why magnetizing current? Due to that the transformer core is magnetized, means flux is developed in that. That's why we call it is magnetizing current. And there we derived EMF equations because of flux in the core is produced. EMF is also produced. Now, what are the EMF equations? What is this equation? Capital E1, E2, RMS equations. Remember, what is the nature of EMF induced in winding? Instantaneous. And that is we converted to RMS. So these equations is RMS equations. 4.44 Bm AN F N1. Similarly, E2 equal 4.44 Bm AN F N2. Okay. Primary induced EMF, secondary induced EMF. So there we have seen some important observations of these EMF equations. Now, there we have seen one important observation that the flux density of the core is proportional to the voltage to frequency ratio. Okay. So one of the observation it is we have seen the flux density of core is proportional to V1 by F ratio, voltage, supply frequency. Very important it is. In all AC machines, you will see this condition, mostly in induction machines, synchronous also. So don't forget this one. Flux density always proportional to voltage to frequency ratio. Now, here there is one important question. Okay, that is, can we operate a transformer can we operate a transformer at low frequency? Suppose just by another way you can take, can we operate the transformer by reducing only frequency? Can we operate transformers by reducing only frequency? Can we operate? We can operate at low frequency, but you should not reduce only frequency here. You should not reduce only frequency. Only frequency should not be reduced. What happen if you reduce? Check it is. See, observe the equation relation. By keeping voltage constant, for example, only frequency I am reducing. By keeping voltage constant, only frequency I am reducing, suppose. Then what happened? Already BM indicates what? Maximum density of core. Based on the rated voltage, based on the rated frequency. It is the maximum density of the core. Now, whenever you reduce only frequency, now what happens to this density increases? Means it is beyond the maximum limit, no? Beyond maximum. Now, what happens to transformer core? Now, transformer core will become saturated. Transformer core will become saturated. Not only transformer core, any iron body, what happened? If you are continuously increasing flux in that iron, electromagnet, suppose, take a electromagnet it is. And when you increase current in this, whenever current or voltage increasing here, current also increases. Whenever current increase, the magnitude of flux will increase or not? Yes, the magnitude of flux in the magnet increases continuously. Now this iron whatever we taken will have some limit or not? Yes, every core, every iron body will have some maximum limit, flux limit. More than that it cannot take. If you increase also it cannot take. Suppose this iron piece can accommodate maximum 100 flux lines, for example. Maximum 100 flux lines it can accommodate. Now, if you are continuously increasing current, flux is trying to increase, but that flux, if once reaches maximum value of 100 flux line, beyond that flux cannot increase in the iron. Even if you increase voltage here, that is completely waste. Okay, even if you increase the current continuously, flux will not increase. No? That means saturation takes place. So once any core saturated, beyond that no variation you can observe. Almost constant flux will be there. Now here also, if you reduce only frequency, no, density increasing. Density means what? What is flux density in terms of flux? Flux per area. Area of core never change, fixed. Density increasing means which one increasing? Flux increasing. The maximum density means maximum flux. Now the flux density here beyond its maximum. Therefore, flux also beyond its maximum limit. Now the transformer core will be saturated. Now under saturation, we should not operate transformers. So what happens if you operate? If you operate transformers under saturation, that is non-linear behavior. No? So with variation of current, flux is not varying. So power transfer also will not take place properly. So we should avoid this operation of transformer. Saturation we should avoid. Saturation should not take place. But I need to operate still at low frequency. How can I operate? I want to operate transformer at lower frequency, but only frequency I should not reduce, because if I reduce only frequency, what is happening? Saturation. So to avoid that, we have one remedy. What is that? Whenever it is required to operate the transformer at low frequency, whenever it is required to operate transformers at low frequency, the procedure is don't reduce only frequency, reduce simultaneously voltage also. Whenever frequency is reducing, reduce voltage also. How to reduce? Such that this ratio should be constant. This ratio should be constant. Suppose previously 400 volt, 50 hertz supply given. Okay, 400 volt, 50 hertz supply given to transformer. Now I need to operate same transformer at 25 hertz for my purpose, to operate some load, for example. Now I need 25 hertz. Then I should not apply same voltage 400. Then what I can do? Reduce the voltage also. How much to be reduced? Such that V1 by F, how much it is? 400 by 50. How much you get? 8. Now that ratio should remain 8 only, like that. if you take 200 volts, 200 by 25, 8 only, then we can operate transformer. So if I want to operate transformer at 25 hertz, you need to reduce the voltage to 200 volts. Then ratio is remains same. There is no variation in the density, means flux also remains same in the core. Then we can operate transformer. Okay. And if it is required to operate transformer at higher frequency, this is not a problem. You can increase the frequency only. No need to touch voltage here. You can increase only frequency, Vm proportional to V1 by F. If you increase frequency, density reduce. That is not a problem for us. Only beyond maximum limit, we should not increase. Reducing, no problem. We can reduce and we can operate transformers. Okay. So remember, only when we are operating transformer at a low frequency, reduce voltage also such that V1 by F ratio is constant in order to avoid saturation of core. Okay, so make a note there, write that point, make a note. In order to operate transformers, in order to operate transformers at low frequencies, in order to operate transformers at low frequencies, reduce the supply voltage also, reduce the supply voltage also, reduce the supply voltage also, such that V1 by F equal to constant. V1 by F equal to constant, comma, to avoid saturation. To avoid saturation. To avoid saturation. Okay. So remember this point, because many times in competitive examinations and also engineering services, we have direct question on this point only. Okay. So let's see one question on this point. Saturation means what? Just now I give an example. No, this iron piece can accommodate only 100 flux line. Every iron material will have some capacity. More than that, it cannot take the flux lines. So in the same way, transformer core can have maximum density of some 1.6 Tesla. Maximum density of the core is 1.6 Tesla, for example. For this much density means you can take example, this core can accommodate 1000 lines, not more than that. The capacity of this core is only 1000 lines. So whenever current increase, flux also increase. At the same time, according to this relation, whenever frequency is reducing, density increasing. Density increasing means which one increasing? Flux increasing. According to this equation, flux increasing. So if the flux lines continuously increasing, maximum 1000 lines only it can accommodate. Now, if you reduce frequency, density increasing. So total flux produced is some 1200 lines. Total flux produced is 1200 lines. But how many lines are there in the core? In the core is flowing only 1000, not 1200. Now the 1200, where is the 200 lines extra? These are wasted, no? So that is not coming into our core. That means already core is saturated. More than that, it cannot accommodate. Saturation means the flux in the core is almost constant. It won't change further. Okay. So we should not operate transformer under saturation condition. So what happened under saturation in the next coming classes, you will see again clearly. Okay. The problems of saturation you will get again. So now you cannot understand. So in the future classes, I will show you what is the problem with the saturation condition. See the question. Read the question. A 200 by 100 volt 50 hertz transformer is to be excited at 40 hertz from 100 volt side. For the exciting current to be same, the applied voltage should be exciting current to be same. Remember, exciting current here means no load current actually, no load current. So still it is not came into picture. So you will see about that no load current after this. Now here exciting current same is magnetizing current should be remain same. Magnetizing current should remain same. So for that, flux density, which is V1 by F, should be constant. Current remains same means flux remains same. Flux remains same means density also remains same. That is V1 by F should be constant. It should not change. Actual the rating of transformer is this 200 by 100 volt. The rating of transformer is 200 by 100 volt and 50 hertz transformer it is. Okay. Now this transformer is to be excited at 40 hertz. Now we need to operate transformer at 40 hertz. Actually it is 50 hertz. Now we need to supply 40 hertz only. And which side it is supplied? 100 volt side. This is important. 100 volt side. For the exciting current to be remain same, the applied voltage should be dash. Means V by F ratio should remain same. Initially, what is the voltage on second 100 volt side? 100 volt, and frequency at that time 50. See, initially, let V11 initial. So actual V1 means primary voltage. And here, what is the primary? Which is the primary? According to the given rating, this is E1, this is E2. Okay. So you can give supply to anywhere, no transformer. Now where they are giving supply? They are giving supply to 100 volt side. 100 volt side. Here they are giving supply. Okay. So directly I'm writing to avoid this confusion. See, previously 100 volts is applied. 100 volts at 50 hertz. So V by F I'm writing 100 by 50 hertz. Now same transformer we need to excite from 40 hertz from 100 volt side. So how much voltage to be applied for this? So this should be equal to V1 by F ratio should remain same, no? Therefore, I need to calculate voltage, how much to be applied now. V by, so this V I need to calculate. This V I need to calculate. V by, what is the new frequency? 40 hertz. So V by F ratio should remain same. Now cross multiply this. So V equal to 80 volts. V means you can consider this is new voltage to be applied on secondary side. 80 volts is need to apply so that V by F ratio remain constant. Okay. 100 volt side it is. 100 volt side they asked. Otherwise, if they ask from 200 volt side, how much voltage we need to apply? Previously 200 volts at 50 hertz. Now new voltage we need to calculate, and how much frequency? 40. Then how much will come? This is V1 equal to 160 volts. Okay, if they ask the same question with respect to 200 volts side, answer is 160 volts. But they are asking with respect to 100 volts side. That's why previously 150 is there, but now how much voltage divided by 40? Yes, 200 by 100 means what? So yesterday observations I given clearly. Whatever the voltage rating given on the nameplate of transformer or in any question, whatever the voltage rating given, that voltage is always E1 by E2. EMF on primary winding and secondary winding. Always E1 by E2 that is. Yes. With respect to 100 volts side, we are calculating, no? That's what. Now, magnetizing current, exciting current, different. Exciting current means actually no load current it is. So you will get in the next coming sessions clearly that is. It is no load current. No load current is the sum of two currents, I naught equal to magnetizing current plus iron loss current. I naught exciting current remains same is I mu remains same. Anyhow, IW constant always. So in the next classes, it will come clearly. Okay. Next question. Next question. So answer for this question 80, because with respect to 100-volt side is this. If the same question is asked with respect to 200-volt side, then answer is 160 volt. Yes. Okay. Next question. See this question. Read the question first. So understanding question important. Read the question with proper understanding. A single phase 50 hertz core type transformer has square core whose circumscribing circle diameter of 40 centimeters. The permissible flux density is 1 Weber per meter square. If the stacking factor is 0.9, the voltage induced per turn is dash. So this is from EMF equation directly. What is the EMF equation first? EMF equation is E equal to 4.44 Bm AN F N. That may be primary or secondary, anything. Okay. Now EMF per turn means what? E by N value, no? E by N we call EMF per turn. What is that value? 4.44 Bm AN F. So this is we need to calculate. So in the given question, permissible flux density, nothing but maximum density of core is 1 Weber per meter square or 1 Tesla, anything. Okay. Bm is there, frequency also there, 50 hertz. Frequency also there, but only the thing is AN is not given directly, but given we can find AN directly not given. In place of that, stacking factor is there. So did you remember stacking factor? What is the stacking factor relation? Ks equal to stacking factor. It is the ratio of net cross sectional area of core to the gross cross sectional area. Okay. So from this AN you can find. What is AN? Ks into AG. Ks is there. Stacking factor is 0.9 given. Ks is 0.9. And AG we need to calculate. Simple one. It is a square core. It is a square core. Square core means actually it is cross section. It is regarding cross section. We have seen two types of cross section. What is that? Square core, stepped core. Square core, stepped core we have seen now. So this is the given square core. Square core cross section it is. Here we place winding. Here we place winding. And what is meaning of circumscribing circle diameter means if you place one turn, how it will come? Like a circle only, no? If you place one turn winding, one turn copper wire is placed, then it is like a circle only forming here. And this circumscribing circle diameter, this diameter given, how much it is? 40 centimeters. 40 centimeters. Now circle diameter, square diagonal, both are same or not? This is a square core, this is circle, and this is 40 centimeter diameter. So this diagonal of square only, no? Yes, both are same. Diameter or diagonal of square, both are same. Now square means all the sides are having same magnitude. Let I am taking it is A, side A. This is also side A, and these are also A. This is also A. Square, all having same magnitude. Length is same. Now, how to find area of a square? Area of a square. What is the formula for area of a square? So here, whatever area you calculate, that is gross area. That is AG equal to, what is the formula I given already? Side square, or whatever length of the side is there, small a, here we taken a square. So that a square you need to calculate. Simple, no? See, this is right angle triangle. Apply right angle triangle. Root of a square plus a square equal to 40 square. This is equal to what? What is the right angle triangle? This is diagonal. 40 equal to root a square plus a square, 40 centimeters. Now square on both sides, squaring on both sides, then we get a square plus a square equal to 40 square. Okay, now 2a square equal to 40 square. Then what is a square directly from this? This is 1600 divided by 2, nothing but 800. Okay, this is a square. A square value is 800. Now substitute here the area of core, gross area it is 800. Okay, 800 centimeters square. Area of gross area of core is 800 centimeters square. Now what we need, AN is required, because in the equation we have AN, net cross section area, that you can find from stacking factor. Therefore substitute here, we will get AN equal to, stacking factor is 0.9 into 800. This is equal to 720 centimeters square. This is AN. Now substitute in this, 4.44, flux density is there 1, and net cross section area 720 into meter square we have to take centimeter, no, it is 10 power minus 4 into F, frequency how much? 50 hertz. Calculate this value. How much it is? 15.9. 15.98 I'm getting. So approximately 16 volts. EMF per turn value, E by N value it is. Voltage per turn or EMF per turn. 16 volts. Yes, right. See, square means it is a laminated core, no? That's why it is AG we taken. Why AG? It is laminated core. That is not given. Anyhow, whatever the cores we are using, laminated only. That's why whatever area you will get, that is gross. Insulation also there in this. But in the EMF equation, we have only net area. That's why AN is calculated. Okay. Not circle area. Why circle area? Because core is a square core, no? Core is square. Only that area we require, not circle area. Stepped core is difficult to find gross area because there are steps. For each step, you need to find separately area. Then you need to add for all the steps. So that based on that, they will give the required data. No? Area is in meter square. That's why 720 into meter, 10 power minus 4 meter square it is. So same I substitute. See, if it is not mentioned laminated also, you need to take laminated only. Otherwise, okay. See, given stacking factor 0.9, what it means? It is a laminated or not? If you remember, while giving statement of stacking factor I given there, equal to 1 means solid core, less than 1 means laminated core it is. So given 0.9, so definitely it is laminated core. So don't get many doubts like this, small, okay? See, 1 centimeter, 10 power minus 2 centimeter square now. So 10 power minus 4. Some of you asking about this formula, how it is. Root of a square plus a square, why root is taken. So in a square, if it is side A, let it is some D. Then what is the formula in this right angle triangle? Just you can apply small relation. Get small d equal to root of a square plus a square. Same thing applied. See, and some of you asking for previous question. Uh, V1 E1 different. V1 E1 they are different, but in most of the numericals, if they don't given any resistance values and reactance value, we consider V1 equal to E1 only. Okay, both are equal, same. Neglecting the drop, that's it. So V1 equal to E1 almost. Okay. If stacking factor is 1, then what you can do, direct whatever area you calculated, that is itself AN. Then directly substitute in EMF equation. Yes. During lamination, definitely that insulation will be there. Those who have that anonymous attendee without names, so try to change your names. Otherwise, I cannot reply anything to you. Aishwarya Venkatesh. ANAG. So did you attend the second class? I think second class one. So there I given ANAG separately. AN means what? Net cross sectional area. AG means gross cross sectional area. And the ratio of these two we call stacking factor. AN is the area occupied by only iron, because when there is a laminated core, this is solid. Laminated means number of thin plates. Each plate is coated with insulating material like oxide paint coating. Then these are all insulation material, insulation cities. So this is iron. See, this is one plate, this is one plate, like number of plates attached together with insulating material. Just like I give an example also, bread pieces and jam. So if you place jam for each piece of the bread and attach all together, then that is laminated. Okay. So if you find here, what is the total area you will get? Gross it is. Gross means total. Now what is net area? It is the area of only this iron material without insulating material. Definitely AN will reduce or not? Yes. So that AN is net cross section area, which is area of only iron material. Okay. Okay, right. See, one thing I observed generally that uh, in normal physical classes, uh, people will not get many types of this type of doubts, but only in online classes from last year I'm observing. So this type of doubts are coming so much. So I don't know why. In normal physical class, no, this type of doubts mostly people will not ask also. Maybe they will get doubt, but they are not asking. But here it is easy to ask. But okay, no problem. You can ask any doubt because we should clarify. We should know, no. Why we are taking an in the formula? So remember, mostly I have given each and every point during the concept itself. This is your concentration only required. Maybe at that time some of you may miss while listening that point. Okay, so an, why we are writing an in EMF equation? Already I said EMF induced. Actually, flux we got here. Flux we got in place of flux phi. We are writing B into A. Okay, anything we can take based on the data given. Phi or BA. BA maximum flux and area. Area means AN I written. Why AN I written? I said EMF is due to flux in the core, and this flux is flowing in the core. In which part of material, iron or insulating material or both? Only in iron flux will travel. No, so flux is flowing only in iron. That is net area, net cross sectional area. That's why I'm not taking AG in this. Clear? Right. Okay, no problem. Any type of doubt you can ask. In the previous question again, with respect to 200 volt, initially 200 volt, it is designed 200 volt, 50 hertz. Suppose if they are same question, how much voltage to be applied for 40 hertz, then how much voltage we need to apply? 200 initially 50. Now how much voltage we need to apply for 40 hertz? So that V by F we applied. So we got 160 volts is the answer. Okay. So we are moving to next question. Next question. This is an important question. Previous gate 2 marks question. So try to do this question yourself first. Read the question first and try to do. At least you should reach important model. So a transformer with a toroidal core of permeability mu is shown in figure. Assuming uniform flux density across the circular core cross section of radius. See, the cross section of core is this small r. The radius of the cross section is small r, and this is mean radius. This is capital R, mean radius, capital R. Neglecting leakage flux, the best estimate for the mean radius, capital R is dash. So given in the first class itself to find the length. So in order to find reluctance, what is the reluctance formula? L by mu A. L is what? Mean length of the core. Length. If it is a square core, we are taking 4 side length. We are doing sum of that. And if it is circular core or toroidal core, how to find the mean length? This length we have to calculate. Circular length. Circular length is nothing but what? Perimeter of circle only. That circular length is nothing but perimeter of circle. So what is the formula for perimeter or length of that perimeter? L equal to 2 pi r. 2 pi r. Okay, so I already given these equations 2 pi r. So we need to find the r relation here. So this is little difficult model because getting idea important. Getting idea important. Most of the people in this year 50% not did this question. So this is nothing but perimeter of circle. Perimeter of circle. That is length L equal to 2 pi r. So R value we need to calculate in terms of that voltages. And here, see, given the sign voltage source of this primary winding is Vp equal to capital V cos omega. Generally, this is of the form what? Sinusoidal, no? Vm cos omega t, like that we are writing, but they given with some different notations. Capital V cos omega it is cos omega t, and primary current given Ip sin omega t because current lags voltage by 90 degrees sin cosine. Okay, this is having turns Np. So this is completely from EMF equation. Completely this solution you will get only from EMF equation. What is EMF equation? First write that E equal to 4.44 phi m, because I'm not writing VA here because flux density not given, but we need the capital R mean radius, which is depends on reluctance. That's why I'm taking phi m directly in the equation. F N. So as it is primary side E1 N1 I'm taking because primary voltage we have. That's why E1 N1. Okay. BA I'm not writing BA here. Why? Because that is not available. Density is not available in the question. That's why I written this equation in terms of phi m. Now E1 equal to 4.44 phi m. How can we write flux in terms of MMF? Flux is MMF divided by reluctance. Okay, into frequency into N1. N1 means here primary terms. So whatever the notations they given, you have to use that. Okay, carefully listen this. What is E1 means? RMS voltage, no? Capital E1 means what? RMS voltage. But here in the question, you don't have RMS voltage. We have instantaneous supply voltage. We have instantaneous supply voltage. What is that voltage here? This is maximum voltage is capital V. Now how to find RMS voltage? How to find RMS voltage? Maximum voltage by root 2. So capital V by root 2. So try to understand one by one it is. V by root 2. E1 means V by root 2. Why it is V by root 2? Actually, they did not given here RMS directly. They given instantaneous in terms of this cos omega t sin omega t. So Vm cos omega t is the standard form. Now what is the RMS voltage? Maximum voltage by root 2. So that V by root 2 I taken. Maximum voltage means here what? Capital V. Okay. Next 4.44 into MMF. What is the MMF? Ampere turns. Current is I and number of turns is, what is the number of turns in this primary? Np. So write that equation. This is the MMF Np into I. Maximum flux, maximum MMF divided by reluctance. So what is the reluctance formula? So write directly. Reluctance is L by mu A. L by mu A into frequency. What is the frequency? frequency is not given in terms of hertz, but given omega. Omega means this is also frequency only. Omega t is what? Frequency in radians per second. Now, how can we write omega in terms of frequency? 2 pi f. 2 pi f. Now, what is the f? Omega by 2 pi. F is omega by 2 pi. Okay. Into n1 primary turns. What is the primary turns given? Np. First, take care of this equation once. Observe carefully this equation. Okay, got it all of this equation? Any doubt in this? E equal to V. How E1 equal to V1 only, no? Because I said there is no resistance drop, nothing given. So directly, most of the cases we take supply voltage only. E1 means supply voltage only. If rating is given, directly you can take, but rating also not given. So whatever source voltage is there, directly that is equated to EMF here. That's why E1 equal to that supply voltage and RMS voltage. Now E1 is RMS, but in the question given Vm cos omega t form. That's why V by root 2 is the RMS voltage of source. Okay. Yes, Sai Ganesh, right. Why current is not taken RMS? Because this is maximum flux. Maximum flux means maximum MMF divided by reluctance. Maximum MMF means N into I, Ni. N is fixed and current is maximum taken. Maximum current is what? This IP. So that's why I said this question little confused and important. Actually, it is Im sin omega t formula in the form of Im sin omega t. Maximum current into sin omega t. What is the maximum current? Capital I. So capital I directly taken. Okay. See, N1 means primary side. That's why N1 equal to NP, not NS. Okay. NS is secondary, na here. Yes, Niharika, right. Option D is correct. See, in the MMF, see, IP you should not write. So all of you following or not, IP we should not write because IP is instantaneous current. What is instantaneous current? Currents are voltages in function of time, omega t, sin omega t, cos omega t, like that. This is of the form Im sin omega t. No, Im is maximum current. So here you have to write maximum flux. So maximum MMF. For that NP. NP means what? Primary. N1 equal to, actual we write N1, but they given NP. Based on the given notation, we are writing. That's it. And NS means what? Secondary side. But we are considering with respect to primary. No, that's why primary I'm writing. NPI by reluctance. Reluctance formula L by mu A. L means this 2 pi r substitute here. Mu keep as it is. A. What is the cross section area of this circle here? Cross section area of circle A equal to pi r square, pi r square, small r square. Given here radius small r, cross section radius is smaller. So area of this is pi r square. That is you have to write. And then finally you will get the capital R relation from this equation. Try to solve. So why we are taking RMS here? Because this EMF equation is RMS equation. That's why we are converting all RMS. Frequency they did not given, no, F. Frequency they did not given F. They given frequency in terms of cos omega t. Omega is there here. Okay. Because of that, I am converting frequency in terms of omega according to the relation omega equal to 2 pi f. In the options also we have omega. Otherwise, if you take direct frequency, you don't get the answers. That's why frequency converted to omega. So substitute all the values first. V by root 2 equal to 4.44 NP into I. Reluctance is L by mu A, 2 pi R divided by mu into A means pi R square. Reluctance into omega by 2 pi into NP. Now we need a best estimation for mean radius, capital R required. Now send capital R to left side and remaining all to right side. So from this first, it will simplify. V by root 2 equal to 4.44. NP become NP square into I into omega into mu into pi R square divided by 2 pi R. But R value required. So for that, solve this. R equal to 4.44 into root 2 divided by 2 pi V into NP square into I into omega into mu pi R square. Pi gets cancelled. Pi R square. That's it. Solve this. Check finally which option will satisfy this. So solve this. Which one will come finally? This option D will come. Right. Mu I R square NP square into omega divided by 2V. So finally, if you solve, you will get this relation. This is the best estimation for mean radius capital R. Okay. Got it all of you same? Yes, yes. So V by root 2 4.44 NP square I omega mu pi R square 2 pi R into 2 pi is there here. Okay. So solve. Finally, you will get this. Solve this. So answer is option D. So this equation will come. See, listen one more time. So we need to find the best estimation for mean radius, capital R we need to calculate. So this capital R, when we'll get capital R here? In the form of perimeter of circle, you will get length equal to 2 pi R. Now from the reluctance formula, what is the formula for reluctance? Mean length by mu into cross sectional area of core. This is mean length. How to find mean length for a circular core or toroidal core here? This is perimeter of circle. That is we applied formula 2 pi r. And area of cross section of the circle is circular core is pi r square. And that small r is the circular core radius. Circular core cross section radius small r. So that is pi r square. Length is mean length or perimeter of the circle 2 pi r. So that is we applied in the formula. And from the RMS equation, EMF equation, E1 equal to 4.44 5 Fn. Now here E1 is not given directly. Generally they will give in the questions now 400 volts by 200 volts. Okay, like that. Some rating they will give, but that is not given. But they given only the supply voltage here. So we are considering that supply voltage itself in place of this E1. Okay, E1 is almost equal to supply voltage only. Directly we taken E1 equal to supply voltage, and supply voltage is also not direct RMS voltage they given. They did not given RMS voltage. They given in the form of this instantaneous voltage, Vm cos omega t form. So what is the RMS value? Maximum value by root 2. What is maximum value from given supply voltage? V. Capital V is the maximum voltage. So V by root 2 taken 4.44. And maximum flux means maximum MMF. Maximum MMF means NI, but that I should be maximum current because maximum MMF required. That's why if you observe the current IP equation, IP also given in form of instantaneous, like Im sin omega t formula it is. What is Im value here? Capital I is the maximum current. That's why I taken divided by reluctance L by mu A. And frequency also they did not mention in the question, but in the option also if you observe the options are in the form of omega only. That's why frequency we converted to omega. What is the formula? Omega equal to 2 pi f. So f is omega by 2 pi. And n1, why n1? Everything we are writing, this equation we are writing with respect to primary side. So n1 is primary turns. So what is primary turns in the given question? Np. That's why np is taken and solved it is, we got the relation for capital R. Okay. Yes, right. Okay, clear all of you. Toroidal core, it doesn't exist means don't tell it doesn't exist. It is there, but practically which one mostly we are using? Toroidal cores we use in auto transformers. But for two winding transformers, mostly toroidal core we don't use. Normal square core or stepped core we use, and that is if you take magnetic circuit, square and shell type mostly we use. Toroidal core, based on the question we have to go. Okay, next. So from EMF equation, these type of questions are important. Direct from EMF equation. Okay, take care of this. So not difficult it is, but getting idea important. Getting idea important for this question. That's it. Only from EMF equation we solve just 3 steps. But all these formulas you should know. Perimeter of circle and area of this cross section, circular core cross section, pi r square. All you should know. Okay, next. Next, the first ideal property we have seen, operation of transformer with the finite permeability core. Now we are going to second ideal property. What is the second ideal property? Iron loss of transformer is 0, but practically possible? No. Now let's consider that. Right side heading, operation of transformer, operation of transformer with iron loss, with iron loss. or core loss of transformer. Okay. Now, whatever we have drawn the figure up to now previous first point, same we are drawing again. Same figure we are drawing again. See this. So I already said step by step we will build these complete concepts. Up to the previous, we will draw same diagram now. So what is that? Previously, the transformer is under no load condition and we are giving a source to the primary, then it is drawing a small current. What is that current? We call magnetizing current. Okay, so when we excite the primary with an alternating voltage source of frequency f, it is drawing a small amount of current, I mu. Now the core is magnetized, EMF induced in this. Core is magnetized. So there is E1, E2 in the primary and secondary windings. So this is up to previous case only. Okay, up to previous diagram we have drawn first. Now observe. Now there is iron loss. Iron loss also we are considering. Practically every core will have a small amount of loss in the form of heat. So due to that, as there is some power loss in transformer, a small amount of power loss. Now we are considering one more current in this called IW. That is called iron loss component of current, or simply iron loss current. Or this is also called working current. That's why we represented it is as IW, working current or iron loss current. Why we taken IW additionally? Suppose if there is no iron loss, IW 0. But now as there is some small amount of iron loss present in the transformer core, that small loss we are representing with one more additional current. Now transformer will draw some additional current from source. Otherwise, just think here. Initially I mu is there, now flux is produced. Now due to that alternating nature of flux, what is the nature of flux passing in the core? Alternating. So as flux is alternating, we have iron loss, which is the sum of hysteresis loss and eddy current loss. So anyhow, we will see clearly about that losses again, hysteresis loss and eddy current. Now anyhow, iron loss is there in the form of what? Heat. Now in order to generate heat, this transformer automatically heat will produce, or it has to take from somewhere. Heat automatically will produce at one body? No. In order to develop that heat, it will consume some power from the source. So as it is consuming, now that is we represented with the current here. That current is IW, iron loss component of current, or working current we call, because it is causing some heat in the core, transformer core. But now, is there two different currents in the same winding? Is two different currents will flow in same winding? No. Suppose if there is a conductor, can you represent here 1 ampere is in this direction, 0.5 amps is in this direction? Can you represent like this? No, blunder. Same current will flow in one conductor, not two different currents at a time. Okay, so this is our just representation. Previously I mu we taken, now IW. But actually under this no load condition, the total current drawn by transformer, under no load is called no load current. Just I naught will flow, and that I naught internally is sum of two currents. One is magnetizing current to magnetize the core, then iron loss current. Now just tell me here, which is first? I mu is first, IW is first. Which is first? Yes, definitely I mu is first. Without I mu, is there IW? If there is no I mu, suppose I mu 0, is there any flux in the core? No flux. If there is no flux in the core, is there any loss in the core? No loss. So no IW. I mu is the first component of no load current. Then IW is the second component. Okay. So totally under no load condition, under no load, secondary side no load, the transformer is drawing a small current from supply. That current we call no load current, I naught. Now this I naught is the sum of two currents. I naught equal to I mu vector addition. Don't take direct sum. Vector addition I mu plus IW is, which is magnetizing current and iron loss current. Now clear? So why we taken additionally IW? If iron loss is set 0 in the question, IW is 0. Okay. So write one point here. Under no load, the transformer is drawing, a small current, a small current IW to represent iron loss of core, to represent iron loss of core, to represent iron loss of core, called as iron loss component of current, iron loss component of current, or working component of current, called iron loss component of current. Enough. So under no load, it is drawing a small current. Previously, I mu is there. Now, what additionally one more current, that is IW, to represent iron loss of core, called iron loss component of current. Now, therefore, right below this, right below this. Therefore, total current under no load, total current drawn by transformer, under no load, is no load is called no load current, is called no load current or exciting current, no load current or exciting current, exciting current, given by I naught equal to vector addition AC. Now it is not DC. If it is DC current, we can directly add. For AC, always vector addition I mu plus IW. So this is I naught. So under no load, transformer is drawing a current called no load current or exciting current, which is the sum of two currents, magnetizing current and iron loss current. See, for induction motor, all these 99% same. The only difference will come there is under no load, induction motor will draw a power that is equal to losses, and additionally one more loss will come in that. Here only iron loss, but in induction motor, same IW, you will see that IWM. Same I naught will become I naught M. So like that, different notations will be followed by different books. So in place of that IW, particularly M will be added. M means what? Additional mechanical loss there. But we don't have any mechanical loss here. Almost same. If you learn well transformer, all these notations, all these equations, induction motor also almost same. Okay. Now write difference between I mu and IW briefly. Right. Difference between I mu and IW. Difference between I mu and IW. Right, I mu, IW. Now, what is the purpose of I mu we taken first? I mu to create flux in the core. So creating flux in any body is a active component or reactive component. So we have what is the total power? Apparent power S equal to active power plus reactive power. Okay. Now this I mu is used or considered to create flux in the core. So flux related anything is what? Reactive component. So tell me one more small question. In your home, in the uh, switchboard, whatever the supply you have, what is that power in that? What is the power in that? Complex apparent power or active power or reactive power? What is the power you are getting in your home? Apparent power, active power or reactive power? Which one? Okay, enough. Okay, enough. Some of you saying active power. The answer is apparent power. The answer is apparent power because from where you are getting supply? Transformer. Don't say that distribution line. Distribution line cannot supply directly. That is not a source. From the transformer you are getting finally. Secondary of transformer you are getting to the loads. So whatever the power is there, that is apparent power, not active power. Now once you switch on the fan, for example ceiling fan, once you switch on the fan, what is the power consumed by the fan first? Active power or reactive power? What is the power consumed by fan once you switch on or once you given supply? That is reactive power, because S is the sum of both, no, active plus reactive. That is reactive power. So what happened there? Once you switch on, it is consuming reactive power in order to develop flux in the motor first. Without magnetic energy here, nothing will happen. So once you switch on, that flux will produce in the fan. Now once there is flux or field, now a torque will develop. Now who will torque? Then active power will come into picture. So once a flux is developed, then torque is produced because of two fields will be there and there is interaction between two fields. A torque is developed and that torque is continuously maintained by active power. Then only active power is enough. That is active power we considered. Reactive power we don't take. So reactive power is very important to create the required flux in any motor. Okay. So I mu is considered to create flux in the core, no? To produce flux in the core. That's why out of these two, I mu is the reactive component of current. So right, first point, it is reactive component, reactive component. And IW, why we take an IW? For representing loss. Power loss is always active power loss or reactive power loss. So have you seen anywhere reactive power losses? No. We have active power loss only. We don't have any reactive power losses. Like we have mainly three elements R, L, C. So out of these three, loss is due to which element? Only resistor. Do you have any loss due to inductor and capacitor? No, they are just energy storage elements. You don't have any losses with that, with the inductor and capacitor. Loss is due to always resistor. So these two are the reactive elements. This is active element. Okay, like that. IW is taken for representing loss. So it is a active component of current. Right, it is. It is active component. It is active component. Okay, next next point. Now as it is reactive component, I mu is reactive. which element is suitable to represent this current. So we need to represent this current in one of the element out of this RLC, which is suitable to represent I mu. Reactive component is suitable. What are the reactive components? Either inductor or capacitor. Now which one we have to take? Inductor we have to take. Why inductor? Because capacitor is related with electrostatic energy. Inductor is related with electromagnetic energy. So what is the energy we have here? Magnetic or static? Magnetic. That's why inductor is suitable for this. Therefore, it is suitable to represent in inductive reactor. So considering an inductive reactor of reactance X naught, that reactance we taken as X naught because no load condition, and this current is represented here, I mu. I mu is represented with inductive reactor. Okay. Next, in the same way, IW. IW is what? Loss. Now, which is suitable for loss? Resistor, definitely. Now, let us consider a resistor of value R naught. And this current is represented here, IW. Okay. Now, clear now up to this. Resistor is taken because loss it is. Loss component. Loss is due to resistor only, not due to inductor or capacitor. So, resistor is taken. Now, out of these two currents, which magnitude is higher? I mu is greater or IW is greater? Tell me. I mu is greater or IW is greater out of these two? Yes, definitely I mu is greater. Why? Because of I mu, IW entered into picture. Without I mu, is there IW? No IW. So I mu is like a source. Due to that only IW is coming. So I mu is little greater than IW always. And for examination point of view, this percentage of current magnitude is important. So I'm writing that percentage. Note down this. I mu is 4 to 5% of full load current. So with respect to full load current, we will compare always. Full load means what? Here load is not connected. Generally, when you connect a load to transformer, it will assume that full load it is. So all these terminology people should be aware. Full load, no load, half full load, all these terminology. Full load means what? Suppose there is a 10 kVA transformer. On the nameplate 10 kVA is there. Means what? The capacity of this transformer 10 kVA. It can supply up to this. Now full load means what? Now you take a load, maybe something motors or whatever it is, heaters. You take a load and that load capacity totally should be 10 kVA. Now the transformer is said to be under full load condition. Now under that full load condition, it will draw some current. Let the full load current is some 100 amperes. For example, 100 amps. So we will see again in the next coming sessions how to find all these full load currents and all. Okay, from the ratings. The full load current is 100 amps, for example. In that 100 ampere, what is the magnitude of magnetizing current in that approximately? That 4 to 5%. Okay, like that. Then IW is little less than this. IW is approximately 1 to 2% of full load current. 1 to 2% of full load current. This percentage is important for competitive examinations, particularly percentage is important. What is the I mu percentage? IW percentage. So I mu little greater than IW always. Next, due to this total current flowing is what? No load current we call. So how to represent that no load current? We should draw these two in parallel. We should draw these two R naught X naught in parallel, because I naught is the sum of two currents. No, this is I naught, sum of two currents. One is I mu, other is IW. This is X naught, R naught. Okay, the percentage of I naught is approximately 5 to 6%. 5 to 6% of full load current. So remember this. So these two are drawn in parallel. R naught X naught is drawn in parallel. Why? I naught is sum of two currents. Then how to represent? Series or parallel? Parallel only. So if you put both in series, R naught X naught, only one current will flow here. Then it won't satisfy. No, that's why it should be in parallel. Then I naught will divide into two parts of current. One is I mu, one is IW. Okay, that's why it is done parallel. So this branch we call no load branch. Remember this branch or this figure, whatever we drawn, this is called no load branch. No load branch. Okay, completed up to this. No, 5 to 6% only. Approximately 5 to 6%. Okay. Shunt parameter. Shunt parameter. I will tell that is in the equivalent circuit because still we did not draw that. Up to now, it is a no load branch only. Load currents will cause copper loss. No load current also will cause copper loss. So it will come in the future. Okay. Next. Equivalent circuit of transformer under no load condition. Equivalent circuit of transformer under no load. This is not complete circuit. Means still we have some more concepts to be complete to draw the complete circuit of transformer. This is up to no load condition only. So this is the circuit. So generally, how we represent transformer? How we represent electrically? Like this, no? This is transformer indication with the two lines here. Just a transformer representation it is. But now we are drawing complete equivalent circuit of this under no load condition. Under no load condition. So under no load, this is no load branch, also called shunt branch because it is always in parallel with the windings. Like this. This is no load. Secondary, we are not connecting any load, open circuit just. And primary side, we are giving a supply voltage V1 and current I1. I1 is no load current, it is no load current I0. Now this I0 is flowing here. I0. The current through resistor is IW, and this is I mu. Okay. See, one important observation I will tell you here. Listen. In this diagram, you should not draw these two lines. So I'm drawing, listen first. You should not draw these two lines in this diagram. What is the representation of these two parallel lines? These two lines represent the core. So transformer may have core, some transformers are air, some of the transformers will have air core. If there is air itself core here means flux will go from primary to secondary through air itself. Through air, flux will go from primary to secondary through air. This is air core. But for air core, the two windings should be very near. and generally we use for some applications like high frequency applications only. This is for general domestic purpose, whatever we are using, all are core type transformers only, not air core. If they mention air core, you should not draw any two lines here. And these two lines represents what? Core. Iron is there. But in this figure, you should not draw this is. You should not draw this is. Why? Why we should not draw? Then it is saying that air core, na it is. If you don't draw, is it air core? No, it is not air core. Why? Because in this diagram, you are indicating I mu and also IW. There is I mu in the figure, there is IW in the figure. That means what? Magnetizing current is there and iron loss current also there. Means core is there or not? Yes, there is a core. Then again, you don't draw these two lines here. Yes, some of the books will draw. Yes, some of the books will draw. Yes, you can draw. But when you draw these two lines, what you need to do is you need to put a small box here. You need to put up to here a small box. Then you have to say this box, in this box, this is a ideal transformer. This is ideal. So here you don't have any currents, nothing. This is ideal transformer. Ideal transformer up to this. This dotted lines indicate whatever is there in the dotted line, that is the ideal transformer. Okay. But when you draw completely, no, then don't draw these two lines, because already with I mu IW, you are saying there is a core. So again, you should not draw these two lines. Otherwise, if you draw, you should put this dotted line, then say this is this up to here, it is a ideal transformer. Okay. Next, from this figure, how to find the values of R naught X naught? Yes, I will tell one more important point, and some of you may get doubt why this I naught or R naught X naught we call no load branch, why it is not drawn like this R naught X naught, why it is not drawn in series with winding like this. No? We have drawn parallelly. We have drawn that R naught X naught parallel with winding, but not series with winding. Why we are not drawing like this? Yes, we should not draw in series because observe what happened. This IW and I mu are the constant currents or variable currents, that you should know. So maybe right now you don't know these are variable or constant. These currents are constant currents. Why constant is? I said in the definition, transformer is a constant flux device. Transformer is a constant flux device. Flux constant means magnetizing current constant or not? Yes, constant. Next, one more. In the transformer, not only transformer, in every machine, iron loss is a constant loss or variable loss. We have mainly two losses: iron loss, copper loss. Copper loss is variable, iron loss is constant. So as iron loss is constant, IW is constant or not? Yes, IW also constant. So as these currents are constants, if you draw in parallel with this supply voltage, then only these two currents are constant. Otherwise, if you draw in series like this, these two will change. So it is wrong. This circuit will be wrong. Why it will change? When you connect load here, the next concept, next part is load operation only. Once you connect load, I2 will flow. Once there is a current I2, the primary current also increases. Now whatever current increase, it will share by these two, R naught X naught. Then that I mu IW is changing, no? Yes. So that they should not change. As they are constant currents, we should represent I mu IW in parallel with supply voltage. Now it is constant. Observe from this figure, tell what is IW? IW, voltage, parallel, na? Voltage is same for both. So voltage is V1 by R naught. Or what is I mu from this? V1 by Jx naught, reactive component. V1 by Jx naught. So you will get now I mu value, IW value. Now they are constant because V1 we don't change, supply voltage. R naught constant, X naught constant, IW constant, I mu also constant. So for this reason, We are drawing I mu IW in parallel with the supply voltage or in parallel with winding, not in series. If you draw in series, these two will not be same constant. They will change under load operation. Okay. Thus people will get doubt why it is drawn parallel, why not in series. Clear all of you? So remember these equations. Every equation we use again in future. All this calculation of IW, I mu, or R naught, X naught also. If it is R naught required, what is R naught from the figure? V1 by IW. If you require to calculate R naught, and if you require to find X naught, V1 by I mu. So we use these equations to find R naught, X naught also. Okay. Next, phasor diagram under no load condition. Already we drawn phasor diagram in previous point. Now total phasor diagram under no load condition, because IW also there now. For that we are drawing phasor diagram. Completed this one. Phasor diagram under no load. Phasor diagram under no load. So up to whatever we have drawn now phasor diagram. So draw same as it is up to previous. So what we have drawn first, supply voltage is first we drawn V1 supply voltage. Then magnetizing current we have drawn I mu, and then flux is produced in phase with current. Then EMF induced lags flux by 90 degrees. This is E1, and E2 also in phase with this. So generally E1 we don't write here because secondary connect loads. That's why we directly take it is E2 only. This is E2. E1, E2 both in phase with different magnitudes. E2 only we are taking. See, in some of the books you will have V1 and E1 also here, E2 also here, like this. So what it means is V1 actually the EMF induced will be opposition to supply voltage according to Lenz's law. Here they should consider like minus E1 minus E2 it is. Then only it is correct. Okay. In some of the books you will see both in phase. V1, E1, E2 all in phase. EMF induced and voltage is in phase. But this will be minus. If they don't given also we have to consider according to Lenz's law it is opposition. Minus E1 minus E2 that is. Okay. Up to this previously we have drawn. Up to this previously we have drawn. Now in the second point, which one will come? IW has came. Now where is that IW? IW. It is a resistive component, no active component. So resistive component is IW in phase with voltage. IW in phase with voltage. So how to draw that IW magnitude? If I mu is this much, just now I given in the differences. What is I mu percentage? 4 to 5%. Then IW 1 to 2%, less than that. That's why the magnitude I drawn less. Okay. Are you observing this I mu IW magnitude? I mu is this much. IW is very small. And why IW is drawn in phase with voltage? Because of resistive element it is. For a resistive element, current is in phase with voltage always. So hope you know that points with a resistor, inductor, capacitor. Okay. Now total current I naught required. What is I naught? Vector addition of I mu plus IW, vector addition. Now how to take that vector addition in the diagram? Simple. From IW, draw a line parallel to I mu. Draw a line parallel to I mu. Next, from I mu, draw a line parallel to IW. Draw a line parallel to IW. So from one vector, draw a line parallel to other vector. Then the intersection point of these two will be the resultant. This is no load current of transformer. This is no load current. So the supply voltage, when we give a current is drawn by transformer, that current is I naught, which is lagging. Observe, this current I naught lags the voltage by some angle. This angle we called power factor angle. What is angle between voltage and current? Always angle between voltage and current always we call power factor angle. So this is a power factor angle, and here we call no load power factor angle because no load condition. This is no load power factor angle. So this angle is generally high, that is in the range 60, 70, 80 like that. So it is 60 to 80 degrees approximately. In this range will be there. High angle it is. No load power factor angle is very high, more than 50 degrees. So if angle is more, what is the cos of that angle? Cos 0, 1. Power factor. What is the angle? Power factor is, we have the power factor range 0 to 1. 0 power factor to unity power factor. Now, if it is cos 60, cos 70, cos 80, power factor is very less. So the no load power factor is almost less than 0.5 always. Remember this. Very less power factor. Particularly for transformer, mostly it is in the range 0.2 to 0.25. 0.2 to 3, let us take. The power factor is in the range 0.2 to 3. Small power factor it is. Very low power factor. Because angle is more. Angle is more. Okay. Now, from this figure, we will get one important relation. Observe this. Observe. Let it is point O, point A, point B, point C. Now, this is a right angle triangle OAB. Now, from right angle triangle OAB. Observe, OAB is the right angle triangle. Okay, OAB is the right angle triangle. Now, from this triangle, we need to find IW, I mu. I naught we have, because in every question you will get I naught value. I naught they will give in question, but I mu, IW values directly they don't give. So you need to find that I mu, IW. How to find? Using I naught you need to calculate. So from this right angle triangle OAB, what is this angle? Phi naught. Now apply cos phi naught. Apply cosine here, cos phi. What is cos phi? Adjacent side by hypotenuse. Adjacent side is what? IW. Hypotenuse is what? I naught. Then you will get IW is I naught cos phi naught. So IW we got. Similarly, apply sin phi naught here. Apply sin phi naught. Apply sin to this angle. Sin means what? Opposite side. Opposite side is AB. Opposite side is AB. But what is AB magnitude? AB is equal to OC, no? Both are same magnitudes. AB equal to OC. What is that OC means? I mu. So this is equal to I mu divided by I naught. So directly I can write I mu by I naught. So just I'm showing opposite side is AB, hypotenuse is I naught. Okay, then I mu we get is I naught sin phi naught. So remember these two equations. IW is I naught cos phi naught. I mu is I naught sin phi naught. Okay, once you know I naught and phi naught value, then you can find I mu, IW using these two equations. Remember this. Okay, got it all of you up to this? Next, make a note below this diagram. So regarding induction motor, I am giving a small point so that easily you can understand. there. Make a note. Note. Suppose if you get this question also important it is. What is the no load power factor of induction motor? No load power factor, cos phi naught of induction motor compared to no load power factor of transformer. What is the relation? Both equal, or no load power factor of induction motor is greater than transformer or less than transformer? Try to guess. No load power factor of induction motor is dash compared to transformer. Greater than, less than, equal. Okay, enough, enough. Okay, enough. So answer for this is less than transformer. Less than it is. No load power factor of induction motor is less than transformer always. So I will tell in the same diagram reason why it is. Observe it. In case of induction motor also same terminology will be there. Magnetizing current will be there. IW, iron loss component will be there. Same as it is. What is the IMU of transformer? We said 4 to 5%, small. But for induction motor, IMU percentage is very high, 25 to 35 percentage. Very high it is. Why very high? Already I said previously. Due to the presence of air gap, reluctance is high. To overcome that, it will take very high current from supply. Okay. And IWM, this is almost same as transformer, like 2 to 4%. 1 to 2% in transformer, but there little increases because mechanical loss added, no? That's why 2 to 4%. Now let's put this variation in the diagram. Put this variation in the diagram. See, approximately I'm drawing, check here itself. This is IMU for transformer. Now for IMU for induction motor will be this much. Very high, now it is 25 to 35%. And what is IW of induction motor? Little increase. 1 to 2%, but little increase for induction motor, little increases. Now if you draw the resultant of these two, then the no load current you will get here. See, IMU is very high. IW slightly increases. For induction motor, these dotted lines. For induction motor is these dotted lines. The resultant of these two is nothing but no load current. Okay, no load current. Now observe what happens to angle here. For induction motor, the angle between voltage current increases or not? This dotted line is the power factor angle for induction motor. Now, whenever angle increase, what is the cos phi naught? So, for example, for transformer phi naught we got 70. For induction motor phi naught we got 80 degrees because more now it is. Why it is increases? Because I mu is very much greater for induction motor. Whenever this I mu increase, your I naught will shift like this. If I mu is increasing, I naught will come towards this. So as I naught is coming towards this or away from voltage axis, the angle increases. Whenever angle increase, power factor decreases. Okay, clear? No load power factor of induction motor less than transformer. Clear all of you? Yes, right. Okay. Let's see one question on this calculation of I mu IW. See this question. So all of you completed this diagram. Okay, right. See the question. A 2000 by 200 volt 50 hertz single phase transformer has exciting current. Exciting current means no load current it is. Exciting current of 0.5 ampere and a core loss of 600 watts when HV side is energized by rated voltage and frequency. The magnetizing current is dash. See, I naught is given in the question 0.5 ampere and core loss given. Core loss means iron loss given 600 watts. 600 when HV side is energized. Energized means supply given to HV side. What is the HV side voltage here? 2000 volts. So directly that voltage itself we take supply voltage. 2000 is the supply voltage. So under no load, I'm drawing figure. See this. Under no load, the transformer is energized or excited from high voltage side. How much voltage? 2000 volts. 2000 volts is given. Actually, E1. So many people may be still in confusion. E1 is 2000, then why supply is 2000? So here almost we take supply voltage also same 2000 volts only, because if it is 2000, now how much voltage you should apply as a source? Can you apply whatever you want? No. Whatever voltage rating is there here, that much voltage you need to apply. That means, okay, 2000 volts. Now when you apply here 2000 volts, it is drawing a current of how much? 0.5 ampere, 0.5 amps. Then there is a iron loss in the transformer. How much it is? 600 watts. So voltage given, current given, loss given, power. Then what is the equation? Iron loss equation. Active power, no, it is. What is the active power equation? VI cos phi. So whatever iron loss is there, this is equal to V naught I naught cos phi naught. Voltage under no load applied, current under no load, cos phi naught, power factor. So just power equation we taken VI cos phi. That's it. Now iron loss is 600. How much voltage applied? 2000 volts rated voltage. And what is the no load current? 0.5 given into cos phi naught. So this is unknown for us. Calculate that cos phi naught from this. How much it is? Calculate cos phi naught. 600 by 2000 into 0.5. So this is 0.6. 0.6. So all of you got same? Yes, now I will raise one small doubt, that is, now some people will get doubt. So just now you said the no load power factor is less than 0.5, but here we got 0.6. How it is? Right? Just now I given here. No load power factor will be mostly in the range less than 0.5. But now in this question we got 0.6. Okay. Are you getting doubt or not? Okay. See, practically the no load power factor is less than 0.5 only. No doubt in that. But numerical wise, I can create any type of question, or you can create any type of question, or some other can create any type of question. So numerical wise, whatever you are getting, try to substitute directly and solve with respect to that data. That's it. And you should not take now 0.6 means it is wrong. I will take less than 0.5. So 0.4 I will take. So whatever numerical is given, solve accordingly. Okay. Don't think very much here. So 0.6. So once you know power factor, or angle you need to calculate, because what we need to find, magnetizing current we need to find. Magnetizing current I mu is, what is the relation? I naught sine phi naught. So sine phi naught we need required. That's why calculate phi naught from this cos inverse 0.6, 53.13. Angle we got a power factor angle. Now substitute here. I naught is 0.5 sine phi naught. Sine 53.13. How much? 0.5. 0.399 or approximately zero point 0.4 amperes. So this is the magnetizing current. Okay. No, zero point 0.5 is the no load current. So already given exciting current or no load current, both are same. Exciting current or no load current. So I mu is magnetizing current, we need to calculate. Okay. Yes, use in degrees only. Use the calculator in degree. In iron loss calculation, some of you asking Wi equal to, this is due to IW, why you taken I naught. So this is V naught into IW only. IW is what? I naught cos phi naught. IW is I naught cos phi naught only, which is iron loss component of no load current. IW nothing but I naught cos phi naught. Okay. See, this iron loss you can find by iron loss. How to find iron loss? This V naught IW, or what is IW? In the previous circuit I written IW V1 by R naught. The V1 means V naught only, because as it is no load, that supply voltage we are considering as V naught, no load voltage. Okay. So V naught into V naught by R naught. What is this? V naught square by R naught. So like this also you can write iron loss. If it is required to find R naught, then use this equation. R naught you will get. Okay. So answer is option D. This type of questions, calculation of magnetizing current, iron loss current, will be there from this one. So let's have some break. After break, we continue load operation. So up to now, what we have seen, no load operation it is. Load is not connected. So under no load, what is the current drawn by transformer? No load current. Now we will see after this load operation of transformer. So take a break for 15 minutes, then come back and we see load operation. For load operation, again phasor diagrams will come. Okay, that is important. So on no load, we don't get any big problems. So on load operation, you will get. Okay, right now. Load operation of transformer. Load operation. Now, whatever we have drawn up to the previous diagram, same diagram I will draw again. Same diagram. So first we consider no load case, then we connect load on this transformer. Now switch is under open condition first. Okay, open means what? No load condition it is. Load is not connected. This is our load. Load is not connected to transformer first. Now at that time, when we give a rated voltage at frequency, it is drawing a current. What is that current we call totally? No load current, which is the sum of I mu IW. Now due to this no load current, EMF induced in two windings because of magnetizing current flux produced. Let this is our main flux. Okay, this is the main flux phi. This is main flux phi under no load condition. EMF induced on both windings E1, E2. There is no current on secondary when switch is under open condition. That is no load condition still. Now let us connect a load and check what happened. Switch is closed. So once you close the switch, means load is connected. Load is connected. Some load. Let us assume some load is connected to transformer. Now whenever load is connected, there is a closure path for current. Now up to that open, no current on secondary side. So there is a current only on primary, that is no load current. Now whenever load is connected, a current I2 is flowing such that how that current I2 will flow? According to Lenz's law, the current I2 will flow such that it will produce a flux opposite to main flux or primary flux. So it will flow in this direction so that the flux will be in upward direction. If you apply right hand thumb rule, current is 4 fingers, thumb indicates flux direction. Therefore, the flux produced is opposite to this main flux. This is the flux due to secondary current. Let the current here is I2. A current I2 is flowing based on the load you connected. I2 is flowing such that it will produce a flux phi 2 in opposite direction of this main flux to satisfy Lenz's law. Now what happened? Whenever there is a opposition from secondary side, automatically the primary transformer primary will draw an additional current from the source. The transformer primary will draw an additional current from the source called I1 dash. It will draw a current I1 dash from the supply in order to produce or compensate the flux phi 2. So previously main flux is there on primary side. Okay, now when there is a current on secondary, whenever load is connected, a flux phi 2 is produced in opposite direction of main flux. Now immediately what happened? A current I1 dash, it is taking from supply. It will take from supply automatically and it will produce a flux. Due to I1 dash, one more flux will produce on primary. What is that flux? That flux is phi 1 dash in this direction. Now this flux phi 1 dash and this phi 2 gets compensated each other. So both are getting balanced. So listen one more time. When load is connected, I2 is flowing. Due to this I2, a flux phi 2 will produce. Now immediately what happened? Instantly, these are all instantly. And instantly what happened at the same time? The primary will draw a current from source. That current is what? I1 dash. This I1 dash we called load component of primary current. Load component of primary current. It will depend on load. It will depend on load. If load increase, this current also increase. Now this current I1 dash will produce one more flux phi1 dash here. So when there is a current, definitely some flux will produce due to that. Now this I1 dash will produce a flux phi1 dash. How much it is? In order to compensate the magnitude of phi2, whatever phi2 will produce, that much again it will produce from primary side, phi1 dash. Therefore, this phi1 dash and phi2 are equal in magnitudes but opposite in direction. Now these two gets cancelled each other. Now finally, what is the resultant flux in the core even under load condition? Under no load, what is flux in the core? Phi. Phi is there. Now under load also, what is the resultant flux in the core? Phi only, because phi2 phi1 dash gets cancelled. So still it is having no load. Resultant flux and in the core is phi only. Due to this reason, the transformer we treated as a constant flux device. It is a constant flux device. Why constant flux? Even under load operation, the flux produced by secondary current and flux produced by primary current compensated each other. So the resultant flux in the core is remains phi only. That's why it is called a constant flux device. So this is in definition I said. This point we left there. So I said it will be shown in the load operation. Okay, now clear why it is called constant flux device. So this is the reason why we call transformer is a constant flux device. If load increase also, or if load decrease also, any case the flux in the core is remains constant. It won't change. Now, so I will tell a small reason how primary is drawing current. So for this, you should little concentrate how flux is produced automatically from primary, because some people may get doubt it is how it is coming automatically phi1 dash. How it is observe carefully. I will show with a separate diagram. So don't bring so many doubts, because if you get like so many doubts for small also, definitely you cannot understand. After listening all, definitely you will forget everything. So up to whatever is required to learn subject, that much only we have to think. But some people thinking very much. So that thinking you have to show in the practicals or in the labs, but we never show there anything, because if you show there, they will remove the marks for us, because internal marks completely with the lab people. Okay. Observe. First, initially under no load condition, it is drawing a current I naught. Then there is only phi in the core. There is a flux phi in the core. So listen carefully. This is phi. Due to that flux phi, EMF induced on primary is E1, E2 is secondary side. Now a load is connected. This is under no load case. Now load is connected, current I2 is flowing. Now what I2 will do? I2 will flow in the winding such that it will produce a flux opposite to main flux. Now what happens to resultant flux in the core? As this phi2 opposing phi, resultant flux getting reducing, no? The flux in the core is getting reducing. So whenever flux in the core is reducing, trying to reduce, then EMF, this E1 also will reduce or not? Yes. This EMF E1 is getting reduced. Voltage is fixed here. Supply voltage is same. Let some 400 volts fixed. Previously under no load, this E1 is almost same. Let 399. Due to that, a small current I naught is there under no load condition. But once you connect load, a flux is produced. That flux is opposing main flux. So resultant flux in the core getting reduced. Now this, as flux is reduced, this E1 is also reduces to some other voltage like 390. Little EMF reduces. Once this EMF reduced, now what happens to this voltage difference? Supply voltage 400, now here 390. Now due to that voltage difference, a current will flow or not? Yes, that current is I1 dash. Now, due to this current, additional flux will produce here phi 1 dash. Then as flux phi 1 dash is produced, it is compensating these two. Now again flux in the core little increases, and that is phi again maintaining. So as flux is constant, that EMF in the winding is almost constant. So like that, whenever load variations are there, it is causing variation of current on primary side also. Like that, primary current increase little, whenever secondary current increasing, whenever secondary current decrease, primary current also simultaneously decrease. So continuously it will happen. So like that it takes place. Okay. Now write some important points regarding this. So clear all of you. So listen one more time. When load is connected, a current I2 will flow on secondary, which produce a flux phi 2. Now, to compensate the flux phi 2, the primary will draw a current I1 dash from supply, which produce a flux phi 1 dash, which will compensate the flux phi 2. Therefore, the resultant flux in the core is phi, which remains constant always. So we call it is constant flux device. Write that points. Write the points. Under load condition, under load condition, a current I2, a current I2 will flow on secondary, will flow on secondary, which produce a flux, which produce a flux phi 2 in the core, in the core opposite to, opposite to main flux, opposite to main flux. Okay. Hence, at the same time, at the same time, the primary will draw a current. The primary will draw, the primary will draw a current I1 dash, I1 dash from supply, from supply, which produce, which produce a flux phi 1 dash to compensate, to compensate phi 2, to compensate phi 2. Therefore, the resultant flux in the core, the resultant flux in the core remains constant. The resultant flux in the core remains constant, which is phi. The resultant flux in the core remains constant. Hence, it is called as, it is called as a constant flux device. A constant flux device. So if load variation also there, still flux in the core remains same. Suppose load increasing said or load decreasing, the flux in the core is same only, it won't change. So different currents, yes, I'm coming to that point only. Now observe. Now come back to the figure. So here I indicated two different currents. Actually, two different currents will not flow. We are representing, but totally the current on this primary side we call I1. I1 only will flow under load operation. That I1 is the sum of two currents. One is no load current plus load component of primary current. Okay. Therefore, the total primary current is what? Vector addition of I0 plus I1 dash. This is the total primary current. Okay. Total primary current drawn by transformer is this much, I naught plus I1 dash. Now phi1 dash phi2 both are equal magnitudes. Now we are writing in terms of MMF. Phi1 dash is due to N1 I1 dash, MMF N1 I1 dash. So MMF by reluctance I am writing just N1 I1 dash by reluctance of core, and phi2 is due to number of turns on secondary N2, N2 I2 by reluctance. Okay. Now reluctance is same core it is throughout that. So directly N1 I1 dash, N1 I1 dash equal to N2 I2. Now if you cross multiply I1 dash by I2 equal to N2 by N1. What is N2 by N1 ratio we call? Transformation ratio. Okay. N2 by N1 we call transformation ratio K. So what is exact value of K? Previously in EMF equation we have seen E2 by E1 equal to N2 by N1. But what is K in terms of current? I1 dash by I2. So what is I1 dash? Maybe in terms of statement if they given, what is I1 dash? Load component of primary current. Based on load, this current is flowing. So load component of primary current divided by load current or secondary current, anything. Okay. But there is a small approximation we do here. Completed. Observe. So we got I1 dash equal I1 dash by I2 is K. From this I1 dash is K times of I2. This is exact relation. I1 dash is K times of I2. But actually what is the primary current? Primary current. Total primary current is I1 equal to I1 dash plus I0. Now what is the value of I0? I0 is a no load current. It is a very small current or not? Compared to load, load currents are very high. No load current is a small current, 5% approximately. But load current is, if we take full load, 100%. So load currents are very high when compared to no load currents. So if you neglect that small no load current, I1 is approximately I1 dash. When it is, since I0 is neglected, I0 is neglected. Small no load current it is neglected. Now when you neglect I1 equal to I1 dash, then what is the K value? I1 by K is approximately, actual K is what? I1 dash by I2. But whenever I0 is neglected, I1 dash is equal to I1 itself. So I1 by I2, approximate it is, not exact. But if you get any question, the exact value of K in terms of current is not I1 by I2. It is I1 dash by I2. This is the exact K. But in general, in all our numericals, we will consider I1 by I2, I1 by I2 in many numericals in the future. So I1 by I2 approximate it is, but not exact. Now, what is the K in terms of voltage? Previously, we got E2 by E1, okay, or N2 by N1. So if you cross multiply this here, E1 I1 is equal to E2 I2. What is E1 I1? Nothing but volt ampere rating. No, voltage current product, volt ampere. Volt ampere rating of input or primary is equal to volt ampere rating of output or secondary. So in the definition itself, I given this is also constant power device. Volt ampere rating of primary winding and secondary winding are same. So this is proof for that. Now that volt ampere same on both sides, is it exactly same? No, it is approximate it is. Why approximate? Actual exact K is I1 dash by I2, but we taken approximately I1 by I2 by neglecting that small no load current. Then only it will satisfy. Okay. The constant power, it will satisfy approximate. Primary volt ampere is equal to secondary volt ampere always in transformer. Okay. Now, what are the types of loads we have? Types of loads means any what type of load we have to connect to transformer. Is it there any condition only fan we have to connect, or only light we have to connect to transformer, or only geysers, or only micro ovens, or only some particular load is there to be connected? No, any type of load we are connecting or not? Yes, in your home itself different types of loads you have. So any type of load you can connect to transformer. So totally we have three types of loads. One is lagging power factor load, leading power factor load, UPF load. Different types of loads. Now based on the type of load you connected, your phasor diagram will change. Now we will draw phasor diagram for all these cases. So from here only the important questions also you will get directly for load operation, particularly for engineering services and competitive examination. For gate point of view, definitely if you get, you will get numerical only on this. That small questions mostly you don't get. But for engineering services and competitive examination, the questions is important from phasor diagram directly. So what are that questions? I will give in the phasor diagram. Observe now. Completed now up to this. All of you completed. Right. Phasor diagram under load operation. So these are not difficult. Already 50% diagram we have drawn. Same diagram again we draw. That is no load diagram, no load phasor diagram. Up to that same for every load. Now based on the type of load we connected, little will change. Phasor diagram under load operation. First case one. Case one. If load on transformer is, if load on transformer, or if load is lagging power factor. Lagging means RL combination, RL load. Let the power factor is cos phi, cos theta 2, cos theta 2, power factor. Some power factor. Example, you can take 0.8 lag, anything, 0.8 lagging, 0 to 1 power factor range. So in that lagging means we take 0.1 lag, 0.2 lag, 0.3 lag, or 0.9 lag, anything. So example, I taken 0.8 lagging, cos theta 2 equal to 0.8, power factor it is. Okay. Now up to no load diagram, draw as it is. That is, what is that? First V1, V1, then magnetizing current and flux in phase with current, then EMF E2, and then IW, and sum of these two will be no load current. This is our no load current. So up to here same for every type of load, it is same. Okay, same diagram up to this, no change. Now load is connected. What is the type of load? Cos theta 2, 0.8 lagging. Now vector direction is anti-clockwise with respect to secondary voltage. Now secondary we are connecting load, so there you need to draw I2. This is our voltage E2. Now where is the current I2? Lags this voltage by some angle. So lagging is left or right. Vectors are in this direction, so current I2 lags means this is. Let this is a current, load current or secondary current I2, which lags voltage by some angle. How much angle? Whatever is there here, theta 2. So cos theta 2 equal to 0.8. Then what is theta 2? 36.86. So theta. Okay, this much angle current lags voltage theta 2. Now in the load operation we have seen when there is a current I2, which one is flowing on primary side? I1 dash is flowing. Then what is the magnitude of I2? I1 dash, just now we have seen this one. I1 dash is always K times I2. K times I2. I2 they will give in the question. So we will solve one question also on this model so that you will understand clearly again. We need I1 dash, which is K times I2. Okay, calculate I1 dash, which is K times I2. So some magnitude you will get here. Now draw that I1 dash. Where I1 dash is flowing? Primary side. Now with respect to the primary voltage, draw exactly opposite to I2. Draw exactly opposite to I2. Exact opposite. Because the flux produced by these two currents are exactly opposite. No? I2 producing phi 2, I1 dash is producing phi 1 dash, exactly in opposite direction. So the corresponding currents exactly opposite we taken I1 dash. This much magnitude K times I2, exactly opposite. And what is this angle here? Theta 2 only. Same angle, exact opposite we draw. Now primary current total. What is total primary current? Vector addition of I1 dash plus I naught. Now draw this I1 here. How to draw vector addition? From one vector, draw a line parallel to other vector. So from here, draw a line parallel to I naught. From I naught, draw a line parallel to I1 dash. Now these two will intersecting here. This is our total primary current. This is our total primary current. Okay. This angle is no load power factor angle, phi naught, and this is theta 2, and this angle is our primary power factor angle. Angle between primary voltage or input voltage, input current is primary or input power factor angle. This is load power factor angle, secondary side. And phi naught is what? No load power factor angle. So don't confuse in all this. Power factor angle means angle between voltage and current. So different currents, so different angles will be there. Okay. So theta 2, load power factor angle. Load power factor angle. Then theta 1, primary or input power factor angle. Primary power factor angle. Phi naught, no load power factor angle. No load power factor angle. Okay. So this is the phasor diagram for lagging power factor load. So first complete this diagram, all of you. Complete this. Why the transformer rating is in volt ampere and all, you will see again in next classes. Completed all of you this diagram. Both currents opposite. Why? I said given no already. The flux produced by these two currents will be exactly opposite direction. They are flowing in primary and secondary. So with respect to primary I1 dash, secondary I2. So exactly opposite they will come. I1 is vector addition of I1 dash and I0. So parallel lines from one other. Parallel lines are drawn and then resultant of these two lines will be I1. After solving problem, your doubt will be clear. Okay. Yes, I2 lags E2. Why it is? So lagging power factor. That's why lagging it is. Why lagging is again? So already heading itself lagging power factor. Current lags voltage. If it is leading, then I2 we take here leads voltage. Now see one important question. First write the question, then we come to this point. Write the question. A transformer is supplying a load of a transformer is supplying a load of 0.866 lagging. A transformer is supplying a load of 0.866 lagging power factor. Okay, then the primary power factor of transformer is dash. Then the primary power factor of transformer is dash. So these are the options. 0.8 lagging, 0.866 lagging, 0.9 lagging, UPF. What is the answer? Answer is dash. Yes, right. Okay, enough. Okay, right. Answer is 0.8 lagging. So directly we can press, no need to solve. And we don't know exact values. Approximately from given data, this will be the answer. Okay, remaining all, if you observe, this is same as given power factor, and remaining 2 is greater than the given power factor. So only one is less than that, that is 0.8. So that is only the answer, because now observe the phasor diagram. Observe the phasor diagram. So from the phasor diagram, theta 1 is greater than theta 2 or not? Theta 2 means what? Load power factor angle. Theta 1 is what? Primary power factor angle. Now theta 1, observe, this is theta 1 greater than theta 2. Theta 2 is this much only. Theta 1 is greater than theta 2. Therefore, what is cos theta 1 now? Less than cos theta 2. Okay. Cosine of that angle will be small. Cos 0, 1. Cos 90, 0. So if angle is more, cosine of that angle will be small value. Power factor is less. So primary power factor is always less than secondary power factor. Remember, in a transformer for lagging power factor only it is. For case 1 lagging power factor only, the primary power factor is less than secondary power factor. So from the given options, which is less than? Only option A, 0.8. Remaining all equal and greater it is. So this is not possible. Okay, make a note. Right. Under lagging power factor loads, under lagging power factor loads, the primary power factor is always less than load power factor. Is less than load or secondary, both are same. Load power factor or secondary power factor is less than secondary power factor. Okay, so directly we are placing option A in this. Next, write one more question. Write one more question. A transformer is operating at a transformer is operating at a lagging power factor, at a lagging power factor. So some value, whatever it is, at a lagging power factor. If The load power factor increases. If the load power factor increases, then primary power factor is dash. Primary power factor is dash. Options: increases, decreases, remains same, remains same. None of this. What is the answer? So increase, decrease, remains same. Tell out of these three, what is the answer? If load power factor increases, primary power factor is dash. Okay, mixed answers. Okay, enough. Enough. Bus. Let's see here. It is also from phasor diagram only. So directly we don't have any conclusions. Everything from phasor diagram only. Now observe the diagram once. Load power factor increases means this is I2 at some lagging power factor, maybe some 0.8. Okay, for example, 0.8. Now, if it is 0.9 lagging power factor, so what we said, load power factor increasing 0.8, 0.85, 0.9, like that. So whenever load power factor increase, the current I2 will come towards voltage. No, I2 will come towards voltage. Then only power factor is increasing. Okay, angle decreases, power factor increases. If I2 is coming in this direction, I1 dash also will move in this direction. I1 dash exactly opposite. No, it will move in this direction. Then I1 also will come little in this direction. I1 also will shift towards this. However, I1 dash is shifting, I1 also will shift towards this. Then if I1 is coming towards voltage V1, then what is the angle theta 1? This is V1. This is I1. Now I1 is coming towards voltage. Now angle is decreasing here. Then what is the power factor? Increases. So if load power factor increase, primary power factor also increase. Answer is increases. Okay, clear all of you this? If load power factor increase, primary power factor also increases. Okay, so write that point here. This is for lagging only. This is for lagging only. So you should take care of these questions, whether they given lagging power factor or leading or UPF, where it is. Okay, this is for lagging only. Write that under lagging power factor. Under lagging power factor, if load power factor increases, then primary power factor also increases. Primary power factor also increases. Vice versa. If load power factor decrease, primary power factor also decrease. Okay. This is for case 1, lagging power factor loads. Now you try to draw case 2, leading power factor load. Right. Case 2. If load is leading power factor. So draw the figure your one first. Case 2. Case 2. If load on transformer, if load is leading power factor load. Leading means RC combination, it is RC loads. Then how the primary power factor will change accordingly. If load is leading power factor, what will be the primary power factor? Draw the figure. Draw the figure yourself and then check it is. In the last question, Pandey, what is confusion? Given that a transformer is operating at some lagging, means you take some cos theta 2 equal to 0.8 lagging at some lagging power factor. Okay. If load power factor increase, then what is the primary power factor? Load power factor increase means what? When power factor will increase, when cos theta 2 will increase, if theta 2 decreases. Then only now. Previously cos theta 2 is 0.8 means 36 degree. Theta 2 is how much? Cos inverse 0.8, 36.86. So whenever that theta 2 is decreasing from 36 to 30, 25, 20, like that. If theta 2 decrease, your power factor means increases. So if you apply this is in the diagram, theta 2 decrease means I2 should come towards this voltage, no? Then only theta 2 will decrease. Suppose I2 is here. I2 is here. Then what is theta 2? Decreases. Then if I2 is coming towards this voltage E2, I1 dash will come towards this V1 now. Both are exactly opposite. However, I2 is there, that I1 dash also will come towards this. Then if I1 dash is approaching towards V1 means I1 also will approach towards V1. Then theta 1 little decrease or not? Yes. Previously theta 1 is this much. But if I1 is coming in this direction towards V1, theta 1 decreases. So whenever angle decrease, power factor increase. Okay. Now clear, Pandey? Okay. Drawn the figure. Check it is yourself. Up to no load diagram, same. Every time draw the same no load phasor diagram. V1. This is I mu. Flux. Secondary voltage E2. IW. The sum of these two we call no load current. Now leading power factor is taken. Example, you can take cos theta 2 equal to some 0.8 lead. 0.8 leading. Now what happens to current? Current leads the voltage here in the vectorial direction, anti-clockwise direction. Now this is the current I2. This is the current I2. Leads the voltage by some angle theta 2, power factor angle. Now when there is I2, I1 dash is flowing. So draw exactly opposite. This is I1 dash. How to find I1 dash magnitude? K times I2. We have the equation. I1 dash is K times I2. Okay, exactly opposite. Now total current is I1 sum of I1 dash plus I0. How to draw resultant? From one vector, draw a line parallel to other vector. Then the intersecting point is resultant. So drawing parallel to I0. And from here, draw a line parallel to I1 dash. Now the intersecting point of these two will give I1. This is I1. Okay. Now the angle between V1 I1 will give primary power factor angle theta 1. So here this I1 is lagging or leading, that depends on these magnitudes. So we cannot say directly always it lags. Sometimes it will lead also. I1 may, suppose if it is V1, maybe some of you may got the figure like this. Check. Maybe you got I1 somewhere here. Okay. Based on the power factor you taken it is. So I am not saying always it is lagging. So in this diagram, I got I1 is what? Lags voltage in the vectorial direction. But somebody may be getting I1 leads. That may be because values we are not taking, approximately roughly we are drawing now. It may be lagging, it may be leading. You cannot say this. Okay. But mostly you will get in the lagging side only, that I1 in the lagging side only, because no load power factor angle is very high. This angle is very high, 70, 75 in that range. Now tell one important question here also. See the question. If load power factor increase, what is the primary power factor? If load power factor increases, then primary power factor is dash. Primary power factor is dash. Increases, decreases, remains same. What is answer? From the figure, tell it is. If load power factor increases, primary power factor is dash. Same as previous analyze. Load power factor increase means what? I2 should come towards voltage. Angle should decrease. Theta 2 should decrease. If I2 is coming in this direction, now I1 dash will come towards V1. Then I1 will go towards magnetizing current. Means I1 is moving away from voltage V1. I1 is moving away from voltage V1 means theta 1 increases. If angle increase, power factor decreases. Okay, just opposite to previous case it is. No need to confuse. Okay, yes, decreases, right? If load power factor increase, primary power factor is decreases. Primary power factor decreases. So that you can observe directly from diagram. Load power factor increase means I2 shifting in this direction. Then I1 dash will come towards V1. Then I1 will go away from V1. Angle theta 1 increase, power factor decrease. Okay. Opposite to lagging it is. Lagging case what happened? If load power factor increase, primary power factor also increase. But here it is opposite. Next, case 3. Case 3. So draw yourself. This is also case 3. If load is UPF, purely resistive load, draw the figure. If load is UPF, draw the figure. Yes, if primary power factor is leading na initially, Siva Gopir, correct. If it is leading initially, then it will increase, but mostly it will come in the lagging only. So very rarely it will come lead. So mostly 90% it is in lagging only. Okay. Yes, yes. So here primary power factor mostly lagging only will come. Lagging only mostly will come. That's why according to that I given this point. If load power factor increases, primary power factor decreases. Okay. V2 is not exactly equal to V2 terminal voltage. E2 is little greater. That depends on power factor. No? So we are neglecting that small drops. Directly we taken E2 equal to V2. Okay. Still we have not considered any resistance drop, any reactance drop. Okay. E1 equal to V1, V1, E2 equal to V2 almost. So have it drawn for UPF case. Phasor diagram for UPF. Case 3. If load is UPF. If load is UPF load. UPF load means what? Purely resistive load or load it is. Now draw the figure for this. cos phi or cos theta 2 equal to 1. UPF means power factor is cos theta 2 equal to 1, theta 2 is 0 degree. Then draw the figure. V1 magnetizing current, flux, EMF, E2, IW, next load is connected. Load is UPF. So current UPF means secondary current in phase with voltage. So I2 is in phase with voltage. I2. Then I1 dash will flow exactly opposite. Exactly opposite I1 dash. Then vector addition of I1 dash and I0 is primary current. Now draw a line parallel to I0 from here and draw a line parallel to I1 dash from here. The intersecting point is I1. Okay, I1. This is theta 1. So even the transformer is supplying UPF load. What will be the primary power factor of the transformer? Is it UPF? No. Still it is under lagging power factor only. Observe, current I1 lags V1 here. Primary is still under lagging power factor only. Current or primary power factor is lagging power factor. Even the load is UPF. Okay. So if the question you will get like this, a transformer supplying UPF load, the primary power factor is dash. 0.8 lagging, 0.8 leading, UPF. What is the answer? 0.8 lagging, because lagging only the answer. Okay. So right, make a note. Note. Under UPF load, the primary of transformer is operating at lagging power factor. The primary of transformer will operate at lagging power factor. Lagging. Now write one more question. Write the question. A transformer supplying a purely resistive load. A transformer is supplying purely resistive load. Okay. Initially it is supplying a purely resistive load. If an inductive load is connected, inductive load is connected additionally, means already there is resistive load, so additionally some more inductive load is connected, RL load. Inductive load is connected, or only inductive load, purely inductive load is connected additionally, then primary power factor is dash. Primary power factor is dash. Options: increases, decreases, remains same. None of this. Tell, out of these three, increase, decrease, remains same. What is the answer? Primary power factor is dash. Initially it is supplying resistive load. Now additionally some more inductive load is connected to transformer, and what happens to primary power factor? Okay, enough. Answer is decrease, right? Enough. Bus. Answer is what? Decreases. Because observe the diagram now. Initially UPF load, current I2 in phase. But when you connect additionally inductive load, then what is overall load power factor? Definitely lagging. There is a R load initially to the transformer. Additionally, some inductive load, that may be RL load or only inductive load, anything some connected. Now, what is overall power factor of load? Definitely it is lagging, no? It will be lagging. Now the overall load power factor will be lagging power factor. Lagging means how this current I2 will shift. Lag means towards left. This is I2. Now current I2 will come towards this because lagging, current I2 lags this voltage. Now if I2 is coming in this direction, I1 dash also will come in this direction. Now I1 will move in this direction. Okay, if I1 is moving away from the voltage V1, angle increase, power factor decreases. So the primary power factor decreases. Okay, suppose if they given in the same case, capacitive load is connected here. Same question, capacitive load is connected. Then what happened? Primary power factor will increase. Okay, if capacitive load is connected additionally to the resistive load, then primary power factor increases. Remember, make a note. Make a note. So tell me the point first. See, I'm giving question, not writing. Just listen and tell the answer. A transformer is supplying UPF load. A transformer is supplying UPF load. Full stop. Question one more time. An ideal transformer supplying UPF load. An ideal transformer supplying UPF load. What is the primary power factor? The primary power factor of transformer is dash. UPF lagging, leading. An ideal transformer supplying UPF load. Then what is the primary power factor? UPF lagging, leading. What is the answer? Okay, most of you right. Yes, enough. Answer is UPF. Answer is UPF because observe the diagram. What I said? Ideal transformer I said. In ideal case, what is the no load current of transformer? Zero. Ideal means it won't take no load current. No load current is zero. Or they will give sometimes no load current is negligible. No load current is negligible or ideal transformer. These are all same. Whenever no load current is neglected, what is I1? I1 equal to I1 dash itself. Actual I1 is this. If you neglect no load current, I1 equal to I1 dash. Then wherever we have I1 dash, that is itself I1. That is itself I1. Now, if load is UPF, primary also UPF. I1 dash equal to I1, no? If I0 is neglected, then I1 is in phase with voltage. So primary power factor also same. So this point, don't forget, mostly up to we complete transformers. What is that? If no load current is negligible or if ideal transformer is given, the primary power factor, secondary power factor, both are same. Okay, write that point, make a note. If I0 is neglected, if I0 is neglected, then primary power factor is equal to secondary power factor or load power factor. Both are same. Secondary or load power factor. Remember this point, never forget up to completion of transformer. So they may say I0 is negligible or they may give ideal transformer, anything same. If they given ideal transformer or if they given no load current is negligible, then primary power factor equal to load power factor. Okay. Anonymous attendee, how means? Just now I given no proof. Means at that time maybe you are not listening. Just now I given why it is same. In the phasor diagram I explained. So first of all, you people should have names, provide names there, not anonymous attendee like this. Now let's see some numericals based on this load operation. In previous gate also we have one question on this. See that. This is previous gate question. This is not only previous gate question, in the recently in AP Transco also in the previous year we have this question, same question as it is given. Read the question first. Read the question. A single phase transformer has turns ratio of 1:2. Turns ratio given 1:2. That is turns ratio means N1 is to N2 given 1:2 or 1/2. And is connected to a purely resistive load as shown in figure. The magnetizing current is I mu equal to 1 ampere and secondary current I2 given 1 ampere. Secondary current I2 is 1 ampere. If core losses and leakage reactances are neglected. Core loss is what? Given neglected. Core loss means iron loss. If iron loss is neglected, IW term is 0 or not? Yes. IW is 0. Core loss given neglected. So IW also should take 0. IW is 0. Then the primary current of transformer is dash. So I1 we need to calculate. Which case it is? Resistive load case. Resistive load. So for resistive load, draw the phasor diagram first. From phasor diagram only we can find easily this. Draw the phasor diagram. V1. See, whenever IW is 0, what is the no load current now? Actual no load current is what? I0 equal to I mu plus IW. But IW is 0 because iron loss is neglected. So I0 is equal to I mu itself. No load current is I mu itself. Okay, so V1, then I mu flux, and then EMF E2. And here IW will not come. I mu itself, I0. Both are same. I mu itself, I0. Then what is the load connected? Resistive load. So as it is resistive load, what is the magnitude of that current given? Load current I2 equal to 1 ampere is given. So current I2 in phase with voltage. This is 1 ampere. Okay. Now I1 dash will flow on primary side. I1 dash. What is I1 dash? K times of I2. What is the K? K. N1 H2 N2 is there. K means N2 by N1. So what is N2 by N1? N2 by N1 is 2 by 1. 2. That is itself K. K value is there. Substitute here. K is 2. I2 is there 1 ampere. So I1 dash is 2 amperes. I1 dash is 2 ampere. So draw exactly opposite. This is I1 dash equal to 2 amperes. Then what is I1? Total primary current we need to calculate, which is the sum of I1 dash plus I0. So I0 is there, I1 dash also there. So draw vector addition of these two. So actually these two are perpendicular. These two are perpendicular. This is our I1. Now this is a right angle triangle only, no? Right angle triangle it is. This is what I mu it is. How much it is? 1 ampere. This is 1 ampere. And how much this one? This is I1 dash. This is I1 dash, same 2 amperes. Now apply that right angle condition. Hypotenuse is root of 1 square plus 2 square. So I1 is this. I1 equal to square root 1 square plus 2 square. This is square root 5 ampere. Root 5 is nothing but 2.24 amperes. Calculate this. So got it all of you this same 2.24 amps. Yes, right. Option C is correct. Option C is right. Not 2 plus 1 because these are vector addition, no, not directly 2 plus 1. Vector addition, root of a square plus b square. Vector addition you have to take. See, what is vector addition? So you people must be perfect in all this mathematical because these are all we cannot learn again here, like anything mathematically. So if there are two vectors, a bar plus b bar, what is the sum of these two? Sum. How we write sum? Root of a square plus b square plus 2ab cos of angle between these two vectors. Vector addition. A bar a square plus b square plus 2ab plus cos of angle between the two vectors. Okay, so that will come in the next question. You will see this. So here also same formula, root of a square plus b square plus 2ab cos angle. What is angle between these two? 90, no, it is. Cos 90 how much? 0. Directly right angle triangle. No need to take directly root a square plus b square. So you should be well in the mathematical calculations. Hmm. 19. Next question. Next. See this question. Read the question. Read the question. This question related to lagging power factor. So we have seen case one, no, lagging power factor load. So that phasor diagram you have to draw here. That phasor diagram you have to draw and put the data given in the diagram. Then try to solve primary current. Okay, this is little lengthy one. Draw the phasor diagram first. Lagging case, first case phasor diagram, draw here. Draw the phasor diagram first. V1, So draw little big diagram so that all numericals you can place well. I mu, flux, EMF, IW, no load current. Now it is lagging case, so current I2 lags the secondary voltage by some angle theta 2. Now I1 dash will flow from primary side, I1 dash. Now vector addition of these two we call primary current totally, I1 dash plus I naught. Now, vector addition. Okay. Now this angles right clearly here. This is no load power factor angle, phi naught. This is no load power factor angle, phi naught. And this is theta 2. Whatever is there, theta 2 load power factor angle, same it is theta 2. And this is theta 1 primary power factor angle. So first read the question now once. A 100 kVA 2400 by 240 volt 50 hertz single phase transformer has a no load current of 0.64 ampere. So given I naught, no load current 0.64 amps. Okay. And a core loss means iron loss is given here 700 watts. So when it is, we got iron loss when its high voltage side is energized, means where source is given, HV side source is given. What is that HV rated voltage? 2400. This is at 2400 volts. This side is given supply at rated voltage and frequency. Now if the transformer supplies a load current, supplying load current is what? I2. Secondary current is how much? 40 ampere given. At what power factor? 0.8 lagging power factor. So cos theta 2 equal to 0.8 lag. Okay, 0.8 lagging. Then primary current is how much? And primary power factor is how much? This is the question. Primary current and primary power factor we need to calculate. Ignore leakage impedance drop. So whenever impedance drop is ignored or neglected, then only V1 equal to E1 and V2 equal to E2. Both are same. Primary side voltages, secondary side voltages will be equal. Impedance drop is ignored or neglected. Okay. First from this, we need to find using this iron loss data, no load power factor angle first. No load power factor angle required for us. So previously also we did one question. Iron loss we equated and their power factor we calculated now. Therefore, iron loss Wi equal to what is the voltage applied? V1, V naught, I naught, cos phi naught. V naught, Vi cos phi. Okay, Vi cos phi. Under no load, the power consumed by transformer is equal to losses. Remember, so these are all will come again in OC test, but for right now we should remember this point. What is that? Under no load condition, whatever transformer is drawing power, that is equal to loss. Why? No load also transformer consuming some power, no? Is there any output from transformer? Are you taking? No output. Output is not connected, but still it is drawing some power. So that power equal to loss, because we have input power equal to output power plus losses always. But what is the output under no load condition? Zero, no output. And whatever transformer is drawing power, input power, that is equal to loss. Which loss? Mainly iron loss. Okay. So iron loss is given 700 equal to how much voltage is applied, which is energized at rated voltage and frequency, high voltage side. So that is I'm substituting 2400 is high voltage, no, into I naught, no load current also given 0.64 into power factor, no load power factor. Now calculate cos phi naught from this. Tell what is the cos phi naught. Cos phi naught how much? 0.45, right? 0.45, okay. 0.45. Then what is angle? Calculate power factor angle. Cos inverse of 0.5. Cos inverse 0.45. Then angle how much? Angle. Yes. 62.8. Yes, right. 62.8 degrees. This is our no load power factor angle. So put all the data here. This is 62.8 degrees. Okay. Theta 2 how much? Load power factor given, no, 0.8 lagging. Then what is theta 2? From here, theta 2 you get. Cos inverse 0.8, 36.86. So this is 36.86. Okay. Now see here. Phi naught is there 62.8. Theta 2 also we have. How much? 36.8. Then what is this angle? Angle between I1 dash and I naught. Angle between I1 dash I naught. How much this angle? 62.8 minus 36.86. Okay, angle difference. Clear all of you from diagram. Phi naught we have 62.8. Theta 2 we have 36.86 load power factor. Then angle between I1 dash I naught you get. Because I1 is what? Vector addition. Just now I given formula. I1 dash square plus I naught square plus 2 I naught I1 dash cos of angle between these two. How much it is? 62.8 minus 36.8. Approximately 26 degrees. No? Okay, 26. Approximately 26 degree. Right. This is 26 degree approximate. Now substituting 26 here. What is I1 dash value? I1 dash we need to calculate. See, I1 dash equal to K times I2. I2 we have 40. Now what is K value first? From the given voltage rating. From the given voltage rating, K equal to E2 by E1 always. What is E2? 240. And E1 is 2400. What is this value? 0.1. So K is 0.1, I2 is 40. So this is 4 amperes. So I1 dash also we have, I0 also we have, then direct substitution in the current. Therefore, substitute all the values and calculate I1. Square root. See, vector addition applied, formula for a vector addition for two vectors. Just now I given now. A bar plus B bar formula is what? Root of A square plus B square plus 2AB cos of angle between the two vectors. That angle we calculated here, 26. Substitute here. I1 dash is 4 square. I0 is how much? 0.64. 0.64 square plus 2 I0 0.64 I1 dash 4 cos of angle between these two is 26. Calculate I1 how much? I1. What is the answer? I1 primary current. Yes, 4.58 amperes, right? Yes, correct. Yes, 4.58 amperes. So primary current we will get from this magnitude. And what we have to find? So anyhow, only one option is there, 4.58, whatever the power factor. So directly we can place. But if there is some confusions given or combinations given in options, then power factor also you must find. Then how to find that power factor? To find the power factor, actually theta 1 required. Theta 1. Theta 1. If you know theta 1, cos theta 1 is primary power factor. So in simple way, we can find the power factor is, see, I1 equal to I1 dash vector addition plus I naught dash. Okay. How can we write this is in the polar form? I1 means I1 at an angle theta 1 equal to, okay, I1 means I1 at an angle theta 1, because V1 is our reference always, supply voltage. This is at an angle 0. So this is theta 1 at an angle theta 1. I1 is at an angle theta 1. I1 dash means I1 dash at an angle. What is the angle for this? Theta 2. Theta 2 plus I naught. What is I naught? I naught is at an angle phi naught. Okay. So A bar nothing but A at an angle theta. So that is we are applying here. Now equate all the real parts. What is A at an angle theta in terms of, this is polar form. What is rectangular form? A into, or A cos theta, A cos theta plus J A sin theta. Okay, real part, imaginary part. So polar form into rectangular form. In the same way, if you expand here, I1 cos theta 1 equal to I1 dash cos theta 2 plus I naught cos phi naught. Now use this equation, you will get theta 1 here, cos theta 1, because primary power factor required. I1 we have now, I1 dash also there, cos theta 2 also there, I naught also there, cos phi naught also there. So substitute all the values in this and calculate cos theta 1 from this equation, primary power factor. Calculate this. I1, what is I1 value? 4.58 into cos theta 1 equal to I1 dash 4 cos theta 2 is 0.8 lagging plus 0.64 I naught cos phi naught is 0.45. Okay, cos phi naught 0.45. Yes, substitute here all the values. Calculate cos theta 1. Calculate cos theta 1. What is answer? Yes, 0.76. Yes, right. 0.76. 0.76. 0.76. Okay. So as much as possible, everyone try to solve every question during the class itself, because I know guarantee that after completion of this, you never open the book, you never practice the questions. Keep assume that this is itself your practice session. Practicing everything, learning, practicing everything is here itself. And you don't get that much time also after completion of total syllabus to practice. But don't take directly here. Maybe it is difficult. Listening continuously 2 hours or 3 or 4 hours means very difficult. I know that. But still try to practice during the class itself. Don't take directly. Take the calculator. In your mobile itself, we have virtual calculators now. So take it and everyone try to solve. then only you will get some confidence on your calculation, because most of the students will prepare very well, but they don't practice properly. And once they attend examination, no, definitely during examination, the calculation mistakes are very, very high. Even they know very well about concept, calculations are not perfect. So they are losing marks. So practice here itself. So surely we will solve nearly 200 questions in transformers, no doubt. Up to total completion of syllabus, nearly 200 questions we will solve. So these questions are enough for your practicing also. So practice during class. Don't blindly take. Okay. And mathematically, you should be perfect in all calculations, all formulas, because we cannot give all the formulas and mathematical equations. Now here again, you should be know very well about this. So this type of questions important from load operation of transformer, maybe lagging load, leading load, whatever they given. This is the procedure to calculate primary current and power factor. Okay. Now observe here, load power factor, how much given in the question? 0.8. And how much you got primary power factor? Less than that you got. How much that is? 0.76. So for lagging power factors, always the primary power factor is less than load power factor. So if you know some concept, suppose they given options now here, like this they given, for example, options they given like this: 4.58 ampere, 0.76 lagging, 4.52 ampere, suppose 4.58 only, 0.8 lagging, 4.58 amperes, 0.86 lagging, 4.58 amperes, zero point 0.9 lagging. Then what will be your answer? If you know now, you no need to find power factor here again. 4.58 you got, current is right, okay. But power factor to find, directly you can put option A, no need to find. Why? Given load power factor 0.8. Then what is the primary power factor? Definitely less than that. Only one option is that 0.76. So remaining all greater than that. So like that concept, if you know well, for some of the questions, by observing options, you can put the answer. No need to take so much time. Calculation time will reduce here. Otherwise, if you don't know that point, you need to calculate for power factor also. It may take again 15-20 seconds. Okay. Okay. Anyhow, in the next class only we start the next property. What is the third ideal property? Third ideal property. Resistance of winding 0, but practically not possible. So in the next class we will take that operation of transformer with the resistance. Okay. So today we stop here. Any doubt? Yes, Naresh Nayak.
Sir,
Hmm.
gross area, net area. In question, how do you know whether they give gross area, net area?
If they given that circumscribing circle means it is what total area, no?
Yes, sir.
It is covering total core. Means whatever you calculated, that is gross only here.
Oh.
Suppose in the question, if they did not given stacking factor,
Hmm.
then you cannot find AN, no? Then you
Yeah.
have to consider this is itself AN if there is no chance.
Okay.
Okay.
Okay, sir.
Next, Rajit Tyagi. See, those who want to ask in Hindi also, you can ask. Hindi में भी पूछ सकते हैं. Rajit Tyagi, Rakesh Kumar.
Good evening, sir.
Yeah.
Sir, once can you tell how reactive power depends, like flux depends on reactive power?
Uh, Depends means we don't have any equation, but anyhow, reactive power in alternators, you will get clearly about this reactive power, active power relations. So there you will see with equations, but here I cannot show directly. But reactive power main purpose is to create flux or electromagnetic energy. It is, that's it. Generally, reactive power we call useless power, active power we call like useful power, no? But
Yes, sir.
reactive power is not useless. That is the most useful because without reactive power, motor cannot rotate.
Okay,
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 you will
sir.
get clearly in alternative topic, that is.
Okay. Sir, can you tell the difference between flux and flux linkages? How they are different, sir? Once can you?
Flux means flux line. Suppose let flux lines is there. Linkages means what? If you pass that flux with a number of turns, then psi is called flux linkages, which is n phi.
Okay.
Flux linkages means with connecting with a number of turns na, at a time.
Yes, sir.
That is flux linkages. Flux means just lines.
Sir, can I say like flux linkages causes flux?
Flux linkages.
Develops flux. Develops.
Yes.
Okay. Sir, and one more doubt, sir. Like if we consider the EMF equation of synchronous machines, alternator, so there we get like a rotation in the rotation causes there what we call flux linkages changes with rotation, no, sir,
Yes.
in synchronous machine. So my
Yes.
doubt is like, sir, can you once write the what I'm telling, sir? EMF is equals to minus d psi by dt, no, sir, there. In
Minus
synchronous machine.
n d phi by d psi by dt means what? Again, we will write there minus psi is n phi, n is taken outside, d phi by dt only. Ultimately, Faraday's law only will come. That is n d phi by dt.
Yes, sir, and d phi by dt, no, sir, like flux here, sir, there we differentiated, no, sir, minus d phi by dt, psi we wrote as n cos omega t, no, sir, in synchronous machines, we'll write.
Because their pole flux will change. Flux we will produce at the poles with chamfering, no cosine. Variation of flux will be there with the pole
Between
shoe
poles.
shape.
Yes, sir.
Yes, yes.
Sir, once what I'm telling once you write, no, sir, minus d psi by dt is equals to, there we write n cos omega t, like n,
Minus
minus
n
d, no, sir, minus in place of psi you write n cos omega t, sir.
minus d by dt of n cos omega t.
Yes, sir.
Uh,
If we use UV rule, we'll get like omega n phi sin omega t minus
omega n phi sin omega t.
minus
Uh,
n cos omega.
Same, almost same equation you will get again. Transformer equation only.
No, sir. It's sir, in a synchronous machine, we consider this first time as dynamically induced EMF. So there
Yes.
we neglect the second term, no, sir.
Yes.
So here in transformers, like second term, if you consider sir, once you write second term, sir, what I'm telling now,
Tell me.
minus n cos minus n cos omega d phi by dt.
Okay.
So here we need to consider this term, no, sir, in transformers.
Not like this, because totally in synchronous machine, whatever the flux is produced, no, actually that is DC, but we are making it is like alternating just by manufacturing pole shape, that is. But here, what is the flux you are producing directly? That is alternating, no, by giving alternating supply.
Yes, sir.
But there in DC synchronous machine, to the rotor field winding, we are not giving any alternating, only we are giving DC excitation. But
Yes.
how the flux is coming alternating there? By using shape of pole shoe, no, that is MMF distribution.
Okay. Okay, sir.
Okay, don't confuse this one.
Yes, sir. Got it. Thank you.
Okay. No. Pranjali.
Hello, sir.
Tell me.
Sir, if transformer is supplying purely resistive load first, then primary will be lagging power factor. And after that, if we connect capacitive load,
okay,
so then the power factor can increase or it can also remain same.
No, if you add capacitive load, then what is overall power factor? Power factor capacitive, no, leading.
But sir, first because of primary, because of resistive load, there is lagging. And then if we add capacitor, then it will be leading. So it can also cancel and it will remain same.
No. See, observe. This is V1, I mu, and E2. So directly I'm taking E2. Then IW, I0. Whenever previously UPF, I2 is here, I1 dash is here, then I1 will be here. Okay. Now, if capacitive load is connected. I2, what is the resultant power factor? Leading. So current I2 leads, no, means I2 will come here. Okay. Then I1 dash will go like this. Then little I1 will come towards this, no. Maybe you are considering it will become UPF and it may also lead. But that much variation will not come. Slightly capacitive load, little added.
Okay. Okay, sir.
Not very much capacitor. Suppose little capacitive load added, then definitely power factor increase here.
Okay, sir.
Okay, if you like that, whatever you are saying, to say like that, we need exact value.
Yes, sir.
Approximately power factor increases just by adding little capacitive load.
Okay, okay, sir. Thank you.
Okay.
Sir,
Tell me.
sir, పవర్ ఫ్యాక్టర్ లీడింగ్ కానీ లాగింగ్ కానీ యూపీఎఫ్ పవర్ ఫ్యాక్టర్ లో కానీ పవర్ ఫ్యాక్టర్ అనేది లెస్ దెన్ 0.8 ఉండాలా సార్?
No, not like that. 0 to 1 actually range of power factor, but practically most of the loads will work in the range 0.7 to 0.9 kada. Mostly we
sir,
consider
కానీ
this.
ఆప్షన్ ఇప్పుడు ఏదైనా క్వశ్చన్ వచ్చినప్పుడు ఆప్షన్స్ లో ఏదైతే లెస్ పవర్ ఫ్యాక్టర్ ఉంటే అదే అని అంటున్నారు కదా.
Yes.
అంటే ఇప్పుడు ఏ క్వశ్చన్ వచ్చినా కానీ లెస్ పవర్ ఫ్యాక్టర్ లెస్ ఉంటే అదే ఆన్సరా సార్?
Not ఏ క్వశ్చన్ అన్న కాదు. If the load is lagging power factor, lagging అయితేనే ఈ condition. If load is lagging power factor, given some 0.8, then what will be the primary power factor? Less than this. అంటే less than 0.8 ఉండాలి. Suppose options given 0.7, 0.8, 0.9 UPF. Then what is answer?
0.7.
0.7, less than. But if load is given leading power factor, then it is not acceptable.
Okay. If the leading power factor it is decreasing, you told no sir, power factor. Then in this case, what happens, sir?
If load is leading power factor 0.8 leading, then if load power factor increase, what happens to primary power factor? So దాన్ని మనం ఫేజర్ డయాగ్రామ్ డ్రా చేసి జస్ట్ అబ్జర్వ్ చేయాలి అప్పటికప్పుడు.
Okay.
Okay. So
Okay, sir.
and one
sir,
more thing.
Yesterday problem, sir.
One.
You gave the 4 points now, sir. Observation of EMF. Last point, E is equals to 4.44 BM ANF N is there, no, sir? N it means turns ratio.
E equal to 4.44 BM ANF N. This is turns only.
If the turns ratio means if the voltage is decrease or increase, it is not a constant, no, sir.
Not clear. Turns ratio means N1 by N2. That you can take as E1 by E2 also.
వోల్టేజ్ వేరీ అవుతూనే ఉంటుంది కదా సార్, అప్పుడు ఇది కాన్స్టెంట్ కాదు కదా సార్ ఎన్ అనేది?
No, N is fixed. That is inside. No, number of turns actually fixed one. Number of turns never you cannot change. So externally to the transformer, what we can change? మనం ఏది చేంజ్ చేయొచ్చు? సప్లై వోల్టేజ్ మ్యాగ్నిట్యూడ్ చేంజ్ చేయొచ్చు, ఆర్ ఫ్రీక్వెన్సీ కూడా చేంజ్ చేయొచ్చు. బట్ ఇన్సైడ్ ఏరియా ఆఫ్ కోర్, నెంబర్ ఆఫ్ టర్న్స్, ఇవన్నీ మనం చేంజ్ చేయలేము కదా.
ఓకే.
Okay,
అంటే వోల్టేజ్ పైన డిపెండ్ అవ్వు కదా సార్ ఎన్ అనేది?
N is fixed. Voltage depends on number of turns. N is fixed always because inside it is. We cannot change. But voltage, if supply voltage change, EMF may change.
అంటే ఇది డిపెండ్స్ ఆన్ వైండింగ్ కదా సార్?
Yes. Flux density I taken V1 by F ratio kada.
Okay, N is depends on winding. How many windings? So that is fixed.
Yes, fixed.
Sir, can you open the transformer, sir?
Which transformer?
Diagram is there, sir.
Total construction, huh?
Is a solid.
It is not there in this page. That is in another file.
Okay, sir. Sir, solid the diagram ఉంది కదా సార్, అది మీరు చూపించారు కదా.
Solid conductor.
అది కనెక్టెడ్, ఆ 2 డయాగ్రామ్స్ అనేది కనెక్టెడ్ అయి ఉంటుందా సార్ సాలిడ్ ది?
ఇది ఏదది ఏ ఫిగర్?
సాలిడ్ అనే ఫిగర్ చూపించారు కదా సార్, ఇట్లా బాక్స్ లాగా వచ్చి సాలిడ్.
కన్జర్వేటర్. ఓకే, యూ మెసేజ్ చేయమని చెప్తాను నేను.
ట్రాన్స్ఫార్మర్ లో ఏ ఆయిల్ యూజ్ చేస్తాం సార్?
We call transformer oil only. We don't have దానికి స్పెసిఫిక్ నేమ్ అంటూ ఏం లేదు, ట్రాన్స్ఫార్మర్ ఆయిల్ అని అంటాం దాన్ని.
ఓకే సార్.
ఓకే, అది ఫిగర్ సెండ్ చేయి, నేను చెప్తాను, చూపిస్తాను.
ఓకే సార్.
రవి కుమార్.
Sir, good evening, sir.
Tell me.
Sir, I had a general doubt, sir. అంటే ఇప్పుడు బయట ట్రాన్స్ఫార్మర్స్ ఉంటాయి కదా సార్, కొన్ని రౌండ్ గా ఉంటాయి, కొన్ని స్క్వేర్ షేప్ లో ఉంటాయి.
దేర్ ఈస్
ఇప్పుడు వాటికి ఏమైనా డిఫరెన్స్ ఉందా సార్? అంటే లోపల వైండింగ్స్
డిఫరెన్స్ జనరలీ పోల్ మౌంటెడ్ లైక్ దిస్ రౌండ్ షేప్ ఉంటాయి కదా కొన్ని. సో వాటిలో సింగిల్ కోరే ఉంటుంది లైక్ దిస్, నాట్ లైక్ స్క్వేర్ షేప్ అండ్ ఆల్ లైక్ దిస్ వర్టికల్లీ. సో దాంట్లోనే ప్రైమరీ వైండింగ్, సెకండరీ వైండింగ్ ఇట్లానే ఉంటుంది ఇండివిజువల్. core is same, windings is located like this because to save the area and to reduce the size and cost of transformer for small voltage ratings or small power applications. So ilantivi use chestam. Generally in rural areas lo untayi ivi.
yes sir. ఇంకొక సార్, అది వైండింగ్ అనేది లింక్స్ మీద చేస్తారా సార్? ఐ మీన్ యోక్స్ మీద చేసినప్పుడు
యోక్ మీదనే చేయొచ్చు, no disadvantage. Yoke also you can do anywhere because square means all are same cross section, no, ఎక్కడైనా పెట్టొచ్చు. బట్ డ్యూ టు సమ్ మెకానికల్ స్టెబిలిటీ మనం ఇక్కడ సైడ్ లో ప్లేస్ చేస్తాం. సో ఇదే స్క్వేర్ ని మీరు ఇలా తిప్పితే ఇది యోక్ అయిపోద్ది కాబట్టి దిస్ ఈజ్ యోక్ అండ్ దిస్ ఈజ్ లిమ్, దీస్ ఆర్ యోక్స్. యూ మేక్ లిటిల్ రొటేషన్ ఎనీవేర్ యూ కెన్ ప్లేస్.
ఓకే, థ్యాంక్ యూ.
శివ.
Hello, sir. Sir, good evening, sir. Page number 1.
Page number
1. Sir, can you explain this question, sir? I have internet connectivity issues, so I can't listen, sir.
Question or this one?
No, this concept you're saying, the reducing frequency.
Okay. Generally, from this EMF equation only, we have this relation. Okay.
Okay, sir.
Whenever it is required to operate any transformer at low frequency, to the transformer you can give any frequency, no, generally first.
Okay.
Any frequency you can operate. So
Okay.
if you want to operate at very low frequency, then if you reduce only supply frequency, no, there is a chance that the transformer core may enter into saturation because flux density will increase, no, there.
Yes,
So
sir.
once saturation takes place, the transformers will draw very high current to maintain the flux in that. Very high current. So it will come in the coming sessions also. It will take very high current, then that currents may cause overheating of the winding and windings may damage. So saturation should not take place. Then what we can do? To avoid that saturation, we have to reduce the supply voltage also.
Okay, sir.
Okay, supply voltage and frequency both reducing so that ratio remains same, saturation will not take place.
Okay, sir. Sir, and then what do you mean by transformer core saturation? So what will happen?
Why?
No, what do you mean by transformer core saturation, sir?
That is only port saturation means suppose you take this is 1 liter bottle or 1 liter can, that is okay. How much water you can pour in this? The size of this scattering is 1 liter, so you can pour 1 liter only, but you have 1.5 liter some liquid. Then if you continuously pour that 1.5, what happened? Overflow will take place, no? Means what happens to that half liter here? Wasted.
Yes, sir.
That is the loss for us. Same thing in transformer core also.
So like it can accommodate only a limited amount of flux.
Yes, more than its capacity it cannot accommodate. Then some loss takes place for us.
Okay, sir. Sir, and then in 12F, sir. Sir, here I0 is a no load current condition.
Why it is flowing under load condition? You are asking.
Yes, sir. Yes, sir. Yes, sir.
Under load also, we have to come from starting, no? Without no load current and magnetizing current, is there flux?
Okay.
No,
Okay, sir.
no. First we started no load, then load is connected. So under no load there is some current. So additionally some more current is flowing. That's why to show that I taken already I1. Otherwise directly I can give I1 is flowing on primary. No.
Yes, sir. Yes, sir.
Okay.
Sir, and then in any practical purposes, we'll connect very like the transformer. I mean, for any practical purposes, we'll start from the first class.
Yes, anything first one.
Okay, sir. So and then here if I0 and I1 dash you know, so two current can't like two current will
Cannot
not
flow
flow
in
the
same winding because actually the two just for understanding purpose step by step we taken. Actually if I don't say like this, no, so load is connected, I2 is there, and directly I1 is flowing, I can give. But what is that I1? Already there is I0 previous, now some additional current is flowing, so totally I1 only it is. Two currents will not flow, I1 only will flow. Okay,
just for representation.
Yes, yes.
Yeah, okay. That's it. Thank you, sir.
Vaishnavi?
Hello, sir. Sir, in 9F, sir, in 9F. సార్ ఇక్కడ లోడ్ బ్రాంచ్ కరెంట్ ని బ్రాంచ్ ని సిరీస్ లో పెట్టకూడదు అన్నారు కదా సార్, ప్రైమరీ రీజన్ ఒకసారి మళ్ళీ చెప్పరా సార్, ఎందుకు పెట్టకూడదు?
ఇఫ్ యూ ప్లేస్ ఇన్ సిరీస్ అండర్ లోడ్ కండిషన్ లో ఇప్పుడు కరెంట్ ఫ్లో అయినాయి కదా I1 డాష్ ఇక్కడ, I1 డాష్ అనేది డివైడ్ అవుద్ది కదా మళ్ళీ ఈ రెండిట్లో, దెన్ IMU IW చేంజ్ అయిపోయినట్టు కదా.
ఒకవేళ ఇలా కనెక్ట్ చేస్తే ఇక్కడ
చేంజ్ అవ్వదు బికాజ్ ఇట్ ఈస్ సప్లై వోల్టేజ్ కాన్స్టెంట్ అక్రాస్ దిస్, రెసిస్టెన్స్ రియాక్టెన్స్ కాన్స్టెంట్, కరెంట్స్ విల్ నాట్ చేంజ్, అండ్ వాట్ ఎవర్ కరెంట్ I1 dash is there that will represented here. Now I1 in the next class it will come, I will show you there. Okay.
ఇంకో డౌట్ సార్, మామూలుగా డాట్ కన్వెన్షన్ ప్యారలల్ ఆపరేషన్ కి యూస్ చేస్తాం కదా సార్, అంటే ఇప్పుడు ట్రాన్స్ఫార్మర్స్ ని ఎట్లా పెట్టాలి సార్, అంటే సేమ్ పొలారిటీ అన్నారు కదా సార్.
One more time.
ఇప్పుడు మనము డాట్ కన్వెన్షన్ ఇస్ రిక్వైర్డ్ ఫర్ ప్యారలల్ ఆపరేషన్ కదా సార్, ప్యారలల్ ఆపరేషన్.
Yes.
అంటే ఇప్పుడు దే షుడ్ హ్యావ్ సేమ్ పొలారిటీ టు ఆపరేట్ అన్నారు కదా సార్ మీరు ఒక పాయింట్ లో.
Yes.
అంటే సేమ్ పొలారిటీ అంటే ఎట్లా సార్, అంటే సబ్ట్రాక్టివ్ పొలారిటీ ఉండాలన్నా అడిటివ్ పొలారిటీ ఉండాలన్నా?
No, same means suppose this is one transformer, primary, secondary, so dots are indicated like this. This is other transformer, primary, secondary, dots are given like this. Now how to connect these two primaries in parallel? So this is supply lines. This is dot connected here, this dot connected here, and undot connected to this wire, undot connected to this wire. Similarly secondary side lines, this is dotted wire, this is connected here, this is connected here, undot is connected to this, undot is connected to this. The same polarities we have to connect in parallel.
సార్ పర్మియబిలిటీ అంటే మీనింగ్ ఏంటి సార్ మామూలుగా, అంటే
just like conductivity.
పర్మిటివిటీ అంటే సార్
మీరు కరెక్ట్ గా మెటీరియల్స్ కి వెళ్ళిపోవాలి, కంప్లీట్ డీటెయిల్స్ కావాలంటే. పర్మిటివిటీ ఆర్ సెలెక్టివిటీ, సో మెనీ వర్డ్స్ ఆర్ దేర్ నా అగైన్.
సార్ ఇప్పుడు మామూలు ఎగ్జాంపుల్ పీక్ వాల్యూ వచ్చేసి 5 volts అంటే ఇప్పుడు మనము పీక్ టు పీక్ వాల్యూ అని అడిగితే 10 volts అని తీసుకోవాలి సార్?
yes only peak means just maximum, peak to peak means maximum to maximum total.
Okay sir.
Okay. Next Sushant Venkanna.
Hello, sir.
Hello, Venkanna. Who is Venkanna? Tell me.
Yeah, sir. I have a general doubt on sir.
Tell me.
Sir, limbs ki under two limbs ki primary and secondary connect chestam kada sir. Why don't we connect limb to yoke?
Two limbs ki primary to secondary.
అంటే ఒక లింబ్ కి ఒక ప్రైమరీ ఇచ్చేసి ఇంకో లింబ్ కి ఇంకో సెకండరీ ఇస్తాం కదా సార్. సో ఒక లింబ్ కి ప్రైమరీ ఇచ్చేసి ఒక యోక్ కి ఎందుకు సెకండరీ ఇవ్వం సార్, అది ఒకసారి చెప్తారా?
అర్థం కాల. టూ లింబ్ మళ్ళీ అడుగు.
ఒకసారి ప్రైమరీకి అంటే 2 లిమ్స్ కి ప్రైమరీ అండ్ సెకండరీ ఇస్తాం కదా సార్.
ఒక లిమ్ ప్రైమరీ,
So,
ఒక
why
లిమ్
don't-
one winding yoke అంటున్నాం.
సో
Yes,
అలా ఎందుకు
we can give, no problem. Anywhere we can give, because if core cross section is same anywhere, all the places, no, you can give anywhere, that is no problem.
ఓకే ఓకే
Just for winding mechanical balance మనం అలా ఇస్తాం core కి. ఎందుకంటే
Okay.
ట్రాన్స్ఫార్మర్ when you lift, it should have equal weight no throughout that.
ఓకే ఓకే
Otherwise, if you place one is here, unbalanced in weight will come.
ఫర్ ద బ్యాలెన్సింగ్ పర్పస్ we should. Okay,
Yes.
thank you sir.
Copper weight is very high.
Okay.
Sir,
Hello.
sir.
Hello.
Who is talking? Dehera.
Hello, sir.
Tell me.
Sir, I have a general doubt, sir. What is the actual use of reactive power?
Just to create magnetic flux. That's it.
Okay, sir.
Reactive
Sir,
power.
then, sir,
Active.
why it is called as a useless power, sir?
Not useless. We creating like that because once motor is started, no, rotating, then which power is consuming motor? Only active power is consuming. That's why we call that is useless. This is useful. But actually, both are very important. Reactive power also important. Without that, no flux production. Then where is the torque?
Okay, sir. Then reactive power is useful for torque production.
Torque means flux production. Because of the field, automatic torque will generate. Because what is the torque? Interaction between two fields.
Okay,
sir. Hello.
Sushant.
Sir, in the first we have did like toroidal problem, sir. Toroidal transform.
Yes.
Sir, like in that problem, why don't we take like IRMS, sir? Like
IRMS means we have to take RMS, but here phi m is what? Maximum flux, no? In the equation, phi m means maximum flux. Maximum flux means what? Maximum MMF.
Okay.
Maximum MMF by reluctance. When you get maximum MMF, number of turns into maximum current.
Okay.
That's why maximum current we take.
Okay, sir. Okay. Thank you, sir.
Sir.
Yugashri.
Sir, ఇప్పుడు కాపర్ లాసెస్ కానీ ఎడ్డీ కరెంట్ లాసెస్ వస్తాయి కదా సార్, ఏ రియాక్టివ్ వల్ల వస్తాయి సార్?
ఏ
రియాక్షన్ వల్ల వస్తాయి సార్?
Copper loss is due to resistance of windings, and whenever current flow అది వస్తుంది కదా, I square R loss.
అంటే
I square R eddy current
ఏమేమి జరిగితే అలా వస్తుంది అని అడుగుతున్నాను.
Eddy current loss is due to flux present in the core. I square R loss only, that is also we call, but that is in the iron core low. But copper loss అనేది ఏంటి? Only in winding. Copper windings లో వచ్చేది I square. That I square R loss we call copper loss.
ఓకే సార్. సార్, సర్క్యూట్ బ్రేకర్స్ అవన్నీ ప్యారలల్ గా కనెక్ట్ చేస్తామా, సిరీస్ లో కనెక్ట్ చేస్తామా సార్?
Parallel only. Parallel, but in series with any load. Parallel only. So all the loads in your home also, everything is in parallel only, no? Fans, lights, everything is in parallel. But there in parallel, suppose there is a AC. In series with that AC, we connect breaker. Okay, load ki series lo breakers ఉంటాయి.
Sir, if any wire is connected in a parallel లో ఉండాల్సింది ఒకవేళ సిరీస్ లో కనెక్ట్ అవుతే అప్పుడు ఏమవుతుంది సార్? రివర్స్ ఫ్లో అవుతుందా లేకపోతే బ్లాస్ట్ అవుతుందా?
ఏది
అంటే ఇప్పుడు సిరీస్ లో కనెక్ట్ చేయాల్సింది ప్యారలల్ లో కనెక్ట్ అయింది అనుకో సార్, ఒక్క వైర్ ఏదన్నా, అప్పుడు అక్కడ వరకే ఫ్లో అవుతుందా లేకపోతే రివర్స్ ఫ్లో అవుతుందా ఒకవేళ బ్లాస్ట్?
If that wire is directly connected between phase neutral, no, then it is a short circuit.
Okay.
Parallel means it may cause short circuit of phase neutral directly.
Okay.
Okay.
Okay, sir. Thank you, sir.
Hello, sir.
Vaishnavi, tell me.
Yes, sir. 19F, in that you explained about unity power factor phasor diagram. Problem you told that if a purely resistive load is there and if an inductive load is connected additionally. So explain that one more time.
Suppose there is resistive load initially, load is at UPF, then what is the primary power factor? Lagging.
Lagging.
Some lagging is there. Now, if you connect inductive load, then what is overall power factor? Lagging only, no?
Lagging.
Lagging means where is the current I2? Here.
Here.
If it is I2, I1 dash also will come here. Then I1 will go towards away from V1.
Yes.
Then what is angle theta 1? Increase.
Increase.
Then cos theta 1? Decrease.
Thank you, sir.
Mukul.
Hello, sir.
Yeah, tell me, Mukul.
Sir, I had a general doubt regarding load of, how we can decide that whether the load is resistive, inductive, or unity.
See,
capacity.
Directly we cannot decide that load side. We should know. Suppose you are at load side, now we know that what we are connecting. Otherwise, suppose if you are looking from input of transformer, you don't know what is the load connected, unless otherwise if you place any meters there.
Okay.
Okay.
But suppose in substation there is one power transformer and it is delivering so much of a load, different types of load. So
definitely in the substation they will have that power factor meter also. It will indicate what is the power factor now it is operating. Suppose if power factor is reducing now, that means that inductive load is very high.
Yes, lagging power.
Like that we can identify.
Okay. And sir, one more doubt, that what is the difference between forced oil cooling and forced air cooling, sir?
Oil cooling, forced oil means they will provide some fan type in the oil itself to force the oil continuously circulating with the quickly. Actually, oil circulation is what very slow through the radiator tubes. But forced oil means we need to provide some motor type or to pressure to circulate that oil quickly in the tube so that quickly heating will reduce. And forced air cooling also same.
Same. Okay.
And we have hydrogen gas cooling also. Sometime if heat is very high, hydrogen gas if you blow on the transformer core and winding, immediately cooling is provided.
Okay. So means we can say that air cooling means we can set up a fan and
yes, air cooling is that.
Okay. And sir, there is one statement here in previous EAC that distribution transformer are designed for minimum core losses. So I didn't get that.
Yes, that will come in all day efficiency, I will tell.
Oh, okay.
Okay.
And sir,
hello, sir.
Sunil, tell me.
Sir, in previous lecture, there is a problem that addition of 100 at an angle 180 plus 200 at an angle minus 300. Sir, how to solve, sir, this? Without calculator, sir, because in our get calculator there is no complex mode, sir.
100 at an angle 180, no? Then what is A at an angle theta formula? A cos theta plus J A sin theta. Okay. Expand like this each one. Then 100 cos 180. What is cos 180? Minus 1.
Sir, minus 1.
Like that you have to expand all this.
Oh, okay, sir. Thank you, sir.
hello, sir.
Mukul.
Sir, here there is one doubt that they are given 12-0-12 volt transformer.
That is tapping, midpoint tapping will be there in that.
Okay.
Okay.
That's what I am confused. What is that?
Okay.
Thank you.
So may not attend for all because still some 10 members are there. Ajay Devidas.
Hello, sir.
Tell me.
Sir, is every time the load changes, the magnitude of E1 changes, sir?
Whenever load changes?
Magnitude of E1, sir, E1.
No, it won't change finally. Steady state it is remains same because flux in the core same, no, almost.
Yes, sir. Okay, to cancel out the అంటే cancel అవ్వడానికి మాత్రమే ఆ కరెంట్ వచ్చి మళ్ళీ నార్మల్ అయిపోతుంది సార్.
Yes, steady state it will వచ్చి.
ఓకే సార్. అంటే అది అంటే ఇప్పుడు క్యాన్సిల్ అయిపోతుంది కదా సార్. అప్పుడు లోడ్ కరెంట్ అనేది ఎలా సప్లై చేస్తారు? అంటే అప్పుడు లోడ్ కరెంట్ ఎలా సార్ ఫ్లో అవుద్ది మరి?
ఆల్మోస్ట్ సేమ్, ఎందుకంటే ప్యారలల్ ఆపరేట్ అవుతాయి కదా ట్రాన్స్ఫార్మర్స్. మిగతా ట్రాన్స్ఫార్మర్ వోల్టేజ్ మెయింటైన్ కాన్స్టెంట్ ప్యారలల్ లో. ద టెర్మినల్ వోల్టేజ్ రిమైన్స్ సేమ్. ఇవన్నీ జస్ట్ ఫ్రాక్షన్ ఆఫ్ సెకండ్ లో అయిపోతాయి.
అంటే అంటే ఇప్పుడు ఒక ట్రాన్స్ఫార్మర్ లోడ్ కనెక్ట్ చేసాం అనుకోండి సడన్, అంటే ఇప్పుడు సెకండరీ క్లోజ్ చేసినప్పుడు లోడ్ వస్తుంది కదా సార్. లోడ్ రావడం వల్ల దాని అపోజ్ చేసిన ఫ్లక్స్ ఇప్పుడు ప్రైమరీ ఈ రెండు అపోజ్ చేసుకుని క్యాన్సిల్ అయిపోతాయి కదా సార్. ఇప్పుడు మళ్ళీ లోడ్ కి మనం సప్లై చేయాలి కదా సార్ కరెంట్. ఇప్పుడు అంటే ఆ కరెంట్ ప్రైమరీ మళ్ళీ అంటే అది 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 ఎలా సార్ మళ్ళీ ప్రొడ్యూస్ చేస్తుంది సార్?
E2 will be fixed, na E2. Secondary EMF will be constant and terminal voltage will change because when load increase, current increase, voltage drop in winding increase, terminal voltage decrease. So like that current will maintain in the load.
Okay sir, E2 okay, E2 is constant so that it will okay. Sir,
yes.
and the doubt sir, 4F sir. Sir, in this in MMF, why should we take only NP sir? Why not both sir in MMF terms sir? NP into I.
That is also I already said no, because MMF is NP into I. What is what that I, no?
No sir, NP into NS. Why can't we write? Why should not?
No, this is completely we are writing with respect to primary winding, no? Secondary open here. There is no source at all in secondary. Source is primary side. So that source ne mana kada మనం substitute చేస్తున్నాం.
Okay sir, secondary is not connect. Okay sir. Okay sir.
మీరు ఏ సోర్స్ అయితే సబ్స్టిట్యూట్ చేస్తారో అదే కరెక్ట్ పెట్టాలి.
Okay sir, thank you sir.
Hello sir.
Tell me, Siddhartha.
In last problem మీరు డైరెక్ట్ కాస్ థీటా అని ఎలా రాస్తారు సార్? అక్కడ సైన్ కాంపోనెంట్ మీరు రాలేరు
ఇక్కడ, అందుకంటే ఇది మనం ఓన్లీ రియల్ పార్ట్స్ ఈక్వేట్ చేసాం కదా. ఏ ఎట్ అన్ యాంగిల్ థీటాలో ఏ కాస్ థీటా, దాంట్లో బి ఎట్ అన్ యాంగిల్ థీటాలో ఓన్లీ రియల్ పార్ట్స్ ని ఈక్వేట్ చేసాం. జస్ట్ ఇమాజినరీ టర్మ్స్ ఈక్వేట్ చేయలేదు. అది అవసరం లేదు కదా మనకి.
ఇమాజినరీ అంటే లైక్ అవి కన్సిడర్ చేయొద్దు సార్?
నాట్ రిక్వైర్డ్. ఎందుకంటే మనకి కొసైన్ అనేది రియల్ పార్ట్ కదా, అందుకని అన్ని కొసైన్ ఈక్వేట్ చేస్తున్నాం. రియల్ పార్ట్స్ అన్ని ఇమాజినరీ పార్ట్స్ అన్ని ఈక్వేట్ చేయొచ్చు ఇఫ్ యూ వాంట్ సైన్ థీటా.
ఓకే ఓకే.
So okay, I'm closing for today. Tomorrow we meet at the same time.
Sir,
Hemant, tell me.
Sir, ఇప్పుడు పవర్ ఫ్యాక్టర్ లీడింగ్ అని తీసుకుంటే మనము ఆర్సీ లోడ్ కనెక్ట్ చేస్తున్నాం కాబట్టి లీడింగ్ అన్నాం కదా సార్. అంటే I2 అక్కడ I2 లీడ్ అవుతుంది కదా సార్ E2 కన్నా. మరి అప్పుడు సెకండరీ వైండింగ్ యొక్క ఇండక్టివ్ ఎఫెక్ట్ ఉండదా సార్?
It will be there. Winding will be inductive only, but load side capacitor connected means what? Generally in power system lo you will get like manaki whenever capacitor load is connected, power factor will improve kada.
అంటే I2 E2 ఎఫెక్ట్ కూడా ఉంటుందేమో కదా సార్? అంటే
definitely it will
లాగ్
be.
అయ్యే ఛాన్స్ కూడా ఉంటుంది కదా.
Yes, it will there. But anyhow most of the loads
లోడ్ ఎఫెక్ట్ ఎక్కువ ఉంటుందా?
ఓవరాల్ లోడ్ మోస్ట్లీ లాగింగ్ ఏ ఉంటుంది. ఎందుకంటే మనం కనెక్ట్ చేసి మోస్ట్లీ లోడ్స్ అన్ని లాగింగ్ ఏ కదా, మోటార్ లోడ్స్ అన్ని. సో
సార్ ఇది పవర్ ఫ్యాక్టర్ పవర్ లో అపరెంట్ పవర్, రియల్ పవర్ అది ఉంది సార్ చెప్తారా?
Generally rating of transformers is in apparent power which is sum of active and reactive. Why it is apparent power and all we will see again. So what is the purpose of active power? Suppose if you take motor load, motor lo em kavali, torque kavali. So who will maintain the torque in motor? Active power. Why? We have power equal to torque omega relation. Okay, torque is maintained by always active power, but do you have Q equal to torque omega? No. So only active power will maintain torque, but not reactive power. But reactive power is just to create flux in motors. The reactive power clearly you will get again in the alternative topics. How to change by changing excitation means flux. We can change the reactive power of generators and motors.
అండ్ ఇప్పుడు లాసెస్ లో హిస్టరీసిస్ లాస్ అంటాం కదా సార్. జనరల్ ఎడ్డీ కరెంట్ లాస్ అంటే 5 వల్ల ఫ్లక్స్ వల్ల కొంచెం సర్క్యులేటింగ్ కరెంట్స్ వస్తాయని చెప్తున్నాను. అంటే హిస్టరీసిస్ లాస్ బేస్డ్ ఆన్ BH కర్వ్ చెప్తున్నాను సార్.
Hysteresis also due to alternating flux only. So how అనేది మనం చూద్దాం.
అంటే మనము BH కర్వ్ ఏరియా ఎక్కువ ఉంటే లాస్ ఎక్కువ ఉందని చెప్తాం కదా సార్ థియరిటికల్. కానీ ఫిజికల్ గా ఎట్లా రిప్రజెంట్ చేస్తాం సార్?
ఫిజికల్ గా అంటే మనం ఫిజికల్ గా చెప్పలేము, బికాస్ దట్ డిపెండ్స్ ఆన్ మ్యాగ్నెటిక్ మెటీరియల్ ప్రాపర్టీ కదా BH. Ferromagnetic, paramagnetic. So ferromagnetic material will have thin BH loop compared to other magnetic materials. So hysteresis loss అనేది తగ్గిపోతుంది automatic. So how it is we will see there. Okay. So okay, good night all of you. So tomorrow we meet again same. Yugashri.
Sir, మనము ఏ పవర్ ఎక్కువ యూజ్ చేస్తాం సార్?
Active power ఏ కదా final consumption. So whatever energy you are calculating, no energy, your power consumption calculated by energy only, no kilowatt hour. Active power.
Apparent power ఎక్కడ యూజ్ చేస్తాం సార్?
Apparent power not like that. That is only the apparent power is total sum of active and reactive, no. So you are consuming the apparent power only, because in your home what you are consuming both active and reactive both you are consuming, but క్యాలిక్యులేషన్ అనేది యాక్టివ్ పవర్ లోనే చేస్తాం. లాస్ అనేది యాక్టివ్ పవర్. ఓకే
ఓకే సార్.
రియాక్టివ్ పవర్ క్యాలిక్యులేషన్ ఉండవు మనకి.
ఓకే సార్.